Large language models are transforming everything from the way we search and write to the way we build software. And if you're a developer, this is your moment. Because behind every AI product, whether it's a chatbot, a tutor, a search agent, is someone who knows how to build with large language models. In this crash course, we'll show you how to become that person. You'll start by exploring how LLMs and APIs really work. Then you'll move on to the OpenAI API with Python. Following that, you'll bring everything together into a complete project, building your own AI application that generates daily personalized meal plans. Your instructor through all of this is Andrei Dumitrescu, a seasoned developer who has taught thousands of students worldwide and has helped many students break into some of the fastest growing areas of programming. But before we get started, we're going to give you a bonus that you're gonna love. Because you're taking this crash course, we're going to give you free access to the Zero to Mastery Discord community. Normally, it's members only, but this means that you can connect with fellow students, star mentors, and even instructors so that you're never learning alone. The invite link is in the description down below. All right, that's it for me. Let me hand it over to Andrei so that you can start building. Enjoy.
Welcome! In this section, we'll dive into the fascinating world of large language models and generative AI. We'll explore what LLMs are, why they are such a breakthrough, and how they generate content that feels human-like. You'll learn about the groundbreaking transformer architecture, especially the attention mechanism, and how it powers these models to focus on the most relevant parts of a conversation. By the end, you'll have a clear understanding of what makes LLMs revolutionary and how they are shaping our digital interactions. So, what exactly are these LLMs that everyone's buzzing about? At their core, large language models, or LLMs, are advanced AI systems designed to process and generate human-like text. Think of them as incredibly intelligent assistants. They are trained on vast collections of text ranging from books and websites to research papers, learning how humans communicate, think, and create. But here's the game changer. They don't just generate information, they understand context. By analyzing patterns in language, they generate responses that feel as though they were crafted by a person. The result? A system that can help you brainstorm, write, and solve complex problems, producing ideas and solutions that have never existed before. Imagine you are preparing for a big team meeting and you type this into ChatGPT. Craft an engaging, ice-breaking activity for our next team meeting that boosts creativity and connection. Within moments, you get a detailed, unique suggestion. A creative activity like a story relay adventure, where each team member contributes one sentence to a story, blending teamwork, fun, and innovation. It's not pulling this from a pre-written playbook. It's generating an original idea based on patterns it learned during training. Why are they called large language models? The name is no accident. The name large language models reflects two key attributes: large and language. These models are trained on massive datasets, sometimes spanning billions or even trillions of words. This scale enables them to grasp the vast diversity of human language and context. At their core, these models are built to work with natural language, understanding and generating text in ways that feel intuitive and human-like. What's the technology behind the magic? How do LLMs work? Let's pull back the curtain and look at the powerhouse technology behind LLMs. Transformers. Transformers are a groundbreaking neural network architecture that revolutionized the way AI processes languages. The secret sauce of these transformers is the attention mechanism. Transformers rely on something called the attention mechanism, which allows the model to focus on the most relevant parts of a text input, whether it's a single sentence or an entire paragraph. Instead of processing all words equally, the model assigns different weights to words based on their importance to the overall context. This focus enables LLMs to generate highly accurate, context-aware responses. You can dive deeper into transformers and the attention mechanisms by reading these Wikipedia articles or even the original papers that are available on arXiv. These papers. Let's move on and talk about the core mechanism: tokens, context, and prediction. Large language models process your input by breaking it into smaller units called tokens. A token can be a word, part of a word, or even just a character, depending on the text and the tokenizer's rules. For example, the phrase "understanding Python" might be split into 3 tokens: under, standing, and Python. We'll go deeper into tokens in the next video. To see exactly how LLMs tokenize text, you can use the OpenAI tokenizer. Using these tokens, the model predicts the next word, phrase, or idea based on the context of the input. This process, called next token prediction, enables LLMs to generate coherent and highly relevant text. The prediction process is what powers GPT. Generative means it creates new original content. Pre-trained means it has already learned from an enormous data set. And transformer is a neural network architecture that enables context-based understanding. One key fact about LLMs is that they do not copy existing content. Instead, they synthesize information from patterns in their training data to produce entirely new and original text. Think of it as remixing ideas into something fresh and customized every time. Let's take a look at an exciting example and visualize it with Gemini. Imagine asking Gemini to create an image based on this prompt. In this case, our request is called a prompt, just tailored for an image generation model. The model processes your words, tokenizes them, and predicts the best visual representation of what you described. I'm requesting ChatGPT the same task. Think of it like training an artist. At first, the artist studies millions of paintings, dissecting brushstrokes, colors, and styles. Over time, they internalize these patterns and begin creating original masterpieces, not by copying, but by innovating. Similarly, LLMs process immense data sets, learning not just to replicate, but to generate unique, contextually rich responses. Let me leave you with this thought-provoking question. What is the fundamental difference between human intuition and AI reasoning? Can AI ever truly replicate or even surpass the depth of human intuition? Okay, to wrap up, in this video, we explored the magic of large language models, how they analyze, generate, and create content that feels human-like. So what's your take on the future of LLMs and Gen AI? In this video, we'll continue discussing the inner working of LLMs and how they function. We'll cover topics like tokens, context windows, and costs. While we'll use OpenAI's models and tools as examples, the same principles apply to other LLMs such as Gemini, Claude, or Grok. Large language models process your input by breaking it into smaller units called tokens. To see how LLMs tokenize text, you can use the OpenAI tokenizer at this address. This tool helps you understand how a piece of text is split into tokens and shows the total token count for that text. For instance, if I paste "learn about language model tokenization" into the tool, it splits the text into 7 tokens. Learn about language model tokenization and dot. A general rule of thumb is that 1 token corresponds to about 4 characters of English text, including spaces and punctuation. This translates to roughly 1/3 of a word, so 100 tokens are approximately 75 words. These tokens count toward what's called the context window of the model, the maximum number of tokens the model can process at once, including both input and output tokens. The context window is also referred to as window size or token limit. For example, GPT-4o has a context window limit of 128k tokens, where the maximum output token limit is 16k, and the remaining tokens up to 128k are reserved for input or the prompt. On the other hand, Google's Gemini Flash models have 1 million token context window by default. This means you can process enormous amounts of information, such as 11 hours of audio code bases with more than 30,000 lines of code or over 700,000 words. You can check out for more details here at this address. This means you can process enormous amounts of information, such as 11 hours of audio code bases with more than 30,000 lines of code and over 700,000 words. As models move toward infinite context length, the potential for seamless, continuous interaction with vast datasets becomes more feasible. It's also important to note that costs are based on the number of tokens processed. For GPT-4o, pricing is typically split between input and the output tokens. For example, as of this writing, OpenAI charges $0.0025 per 1K input tokens and $0.01 per 1K output tokens. Let's do the math for an example. If you submit a 250 token input, about half a page, and receive a 1000 token response, roughly 2 pages, the cost would be $0.0025 divided by 4 plus 0.01, which is approximately 1 cent for this interaction. Note that this is quite inexpensive, especially considering that GPT-4o isn't the cheapest model available, and costs are continuing to decrease over time. In this lesson, you learned about the concept of tokens, how they are counted, and their importance in defining the context window of a language model. We also covered how token limits affect the amount of input and output text an LLM can handle, and how the cost of using LLMs is calculated based on token usage. Understanding these details will help you use LLMs more effectively, whether you are crafting inputs, estimating costs, or building applications with LLMs. In this video, we are exploring a fascinating topic that's transforming the way we interact with AI: LLM APIs. These tools make it easier than ever to build intelligent AI-powered applications with just a few lines of code. Here's what we'll cover. We'll start with a quick introduction to APIs, what they are, their advantages, and examples from everyday life. Then, we'll dive into LLM APIs, specifically focusing on providers like OpenAI, Gemini, and Anthropic, and why they are so powerful. Finally, we'll work through a practical example using OpenAI's GPT-4o model to demonstrate how easy it is to get started. By the end, you'll know how to use these LLM APIs to bring the power of AI into your Python projects. Before diving into LLM APIs, let's step back and define what an API actually is. API stands for Application Programming Interface. Think of it as a bridge that allows two software systems to talk to each other. For example, a weather API lets you fetch real-time temperature and forecast data. A stock exchange API provides live market prices and historical data for financial analysis. What's great about APIs is that you don't need to build everything yourself. You simply connect to a service that provides the functionality you need. It saves time, simplifies development, and ensures you are using reliable, scalable systems. Now, just as there are APIs for weather and stocks, there are also APIs for large language models. These let us use cutting-edge AI models like OpenAI's GPT, Google's Gemini, or Anthropic's Claude without worrying about the infrastructure or training process. LLM APIs are part of a broader trend called AI as a service. Here's how it works. Providers like OpenAI, Google Gemini, and Anthropic maintain enormous AI infrastructure. This infrastructure includes massive servers, GPUs, TPUs, and other advanced hardware. For example, Google uses TPU v4 pods that can perform quadrillions of operations per second. Instead of buying this hardware and training the models ourselves, many of which are proprietary, we access these services via APIs and pay only for what we use. Note that it would be nearly impossible, even for a large company, to maintain such infrastructure, as training GPT-4 alone costs tens of millions of dollars. The pricing is typically based on input and output tokens. A token is a unit of text, such as a word or a piece of punctuation. For example, generating a few sentences might cost a few fractions of a cent. This makes it highly cost-effective and scalable. What makes LLM APIs so powerful? LLM APIs offer incredible benefits. Easy of access. You don't need to train or manage your own AI models. Versatility. They can handle text, image, or video generation, summarization, translation, and even coding. And scalability. Whether you are prototyping a small project or building a large-scale app, these APIs can handle it. For Python developers, they are a game changer enabling you to integrate advanced AI capabilities with minimal effort. Let's see how easy it is to use one of these APIs in Python with a practical example. We'll make an API request using OpenAI's GPT-4o. This model is multimodal and powerful, making it ideal for many applications. Here's the step-by-step process. I'm starting from scratch, so I'm installing the OpenAI API library, which gives us access to OpenAI's infrastructure and models. I'm running pip install OpenAI. Now, let's get coding. I'm pasting the code, and then I'll walk you through it step by step. We covered everything shown here, including importing modules, defining and calling functions, and creating and working with dictionaries and lists in previous sections. Take a look there if you feel the need. First, I'm importing the OpenAI class from the OpenAI library. This will give us access to all the tools we need to interact with OpenAI's API. Next, we are setting up the API key. This is like our secret password that lets us securely access OpenAI's services. In a real-world project, you'd want to avoid hard coding the API key like this. Instead, you might store it in an environment variable or a configuration file. Note that I signed up for a new account and generated the key before. Now, we are initializing an OpenAI client. This client is what we'll use to send requests to the API and receive responses. Next, we define a function called askAI that takes the prompt and the temperature as parameters. For the temperature, we use the default value of 1. This function will make it easier to send questions to the API without repeating the code. Here, we are creating a chat completion. This means we are asking OpenAI's model to generate a response based on a conversation style input. We are specifying the model we want to use for this task. The message parameter defines the flow of the conversation so far. I'll go deeper into chat completion's API later on. This is the prompt and represents what the user, you, is asking the assistant to do. The temperature parameter controls the randomness of the AI's responses. A higher value like 1 makes the output more creative and diverse. Finally, we are returning the AI response. The completion object contains all the information returned by the API. Very well, I am running the code. Let's send the first question. We want the AI to provide a poem about a lonely robot. I'm running the code. In a few seconds, we'll get the response. A poem about a lonely robot exploring a futuristic city. Very nice. Let's ask something very interesting. If AI can fully replace humans. I am running the code. As you can see, we interacted with one of the most powerful models using just a few lines of code. That's the power of an API. This brings us to the end of this video. To recap, APIs are bridges between applications, saving time and resources. LLM APIs offer AI as a service, letting you harness powerful language models without managing infrastructure. We walked through a practical example using OpenAI's GPT-4o to create an original poem or to answer philosophical questions. In the next video, we'll dive deeper into specific use cases for LLM APIs and how to fine-tune your AI-powered applications. Until then, happy coding! Welcome back. In this video, we'll explore three pivotal platforms in AI landscape: OpenAI Playground, Google AI Studio, and Anthropic Console. We'll dive into their sign-up process, prototype creation capabilities, and user interfaces. By the end, you'll have a clear understanding of how to leverage each platform effectively. These platforms, OpenAI Playground, Google AI Studio, and Anthropic Console, offer unique features for AI prototyping and development. To access OpenAI Playground, visit platform.openai.com and sign up for a new account. The sign-up process involves providing your email address, creating a password, and verifying your email address. After signing up, you'll need to add a credit card and purchase some credits to start using the API. Although this requires a small investment, using the OpenAI models is very cost-effective. Testing everything included in this course should keep your total budget under a few dollars. I'm logging in. Once logged in, navigate to the Playground section. This is a simple yet powerful environment where you can experiment with OpenAI's language models by entering prompts and observing the outputs. It's perfect for testing ideas and understanding how these models behave. The interface features a minimalistic design with a clean text input and adjustable parameters like temperature and maximum tokens. You can easily test different prompts and settings to see how they affect the model's responses. Next, let's talk about Google AI Studio. Visit the Google AI Studio website at ai.google.dev and sign in using your Google account. If you don't already have one, you'll need to create it. Once signed in, you'll land on the dashboard where you can create new projects, explore various AI tools, and manage your existing projects. Google AI Studio provides access to a range of models, including Gemini, which supports multimodal inputs like text, images, and more. Unlike OpenAI, Google AI Studio and Gemini are free of charge under certain usage limits, making them a great choice for experimentation without upfront costs. This comprehensive dashboard offers a wide variety of tools for AI development with intuitive navigation and project management options. Lastly, we have the Anthropic Console. Visit the Anthropic website and sign in using your Google account or an email address. After logging in, you'll gain access to the dashboard and the Workbench, a web-based interface to Claude, Anthropic's LLM. The Workbench is similar to the OpenAI Playground and is designed for prototyping and testing API calls. It provides sections for user input, system prompts, and model responses, making it an excellent tool for refining your AI applications. To use Anthropic's API and Workbench, you'll need to add billing information and buy usage credits. After funding your account, navigate to the API keys section and generate a new key. With this key, you can integrate Anthropic's language models into your applications and utilize them within the Workbench. In this course, we'll discuss OpenAI and Gemini models. In the rapidly evolving field of artificial intelligence, various models are developed to tackle complex tasks. These models undergo rigorous testing to evaluate their performance, robustness, and generalization capabilities. Chatbot Arena is an open platform for crowdsourced AI benchmarking where users can cast their votes to help improve AI evaluation. The platform ranks the best LLMs and AI chatbots. Check out this page from time to time to see which models are the best and what new models have been launched. This brings us to the end of this video. In summary, OpenAI Playground, Google AI Studio, and Anthropic Console are powerful environments for AI development. OpenAI and Anthropic require setting up billing, but they are cost-effective options. Google AI Studio includes Gemini and offers free experimentation within its limits. Thank you for watching this video. Keep exploring, keep coding, and continue your journey in the exciting world of AI with Python. See you in the next video. Have you ever wondered why sometimes a language model like GPT gives you a perfect answer and other times it feels like it's completely off? Or maybe you've asked it for a solution but it returned something that just didn't make sense. Or even worse, it confidently delivered an incorrect response. In this video, we are going to uncover the hidden challenges and limitations of large language models that every Python developer working with Gen AI needs to know. We'll discuss their over-reliance on training data, challenges with accuracy and hallucinations, the ethical concerns they raise, and practical limitations like token size and computational costs. By the end of this video, you'll have a solid understanding of the challenges LLMs face and how to navigate them like a pro. Let's dive in. The first LLM issue we are going to talk about is hallucinations and fabricated responses. No, we are not talking about sci-fi here. Hallucinations in LLMs refers to the phenomenon where the model generates responses that sound plausible but are completely fabricated or incorrect. For example, ask an LLM about an initial library or programming technique that doesn't exist, and it might confidently generate code and documentation for it. In this example, data frame X doesn't exist. Imagine deploying that in production. It's a disaster waiting to happen. In this example, I am asking about an introduction to data frame X, a non-existing library, and the ChatGPT provides a completely fabricated answer. You cannot rely on LLMs as the sole source of truth. As a best practice, always validate critical outputs. Use knowledge grounding techniques such as retrieval augmented generation, where the LLM retrieves verified information from a trusted database or source. Next up, biases in outputs. LLMs inherit biases from their training data. For example, they might favor one viewpoint over another, or unknowingly produce outputs that reinforce stereotypes. For example, if you ask for career advice, the model might suggest traditionally male-dominated roles for men and female-dominated roles for women, simply because the training data reflected those biases. Or, when asked to describe a traditional wedding, the model might prioritize Western-style weddings over other cultural traditions due to the predominance of Western data in its training set. As a best practice to avoid biases, you can start by making sure that your training data is diverse and balanced. Tools detecting bias, along with fairness-focused techniques, are super useful for catching issues early. It's also important to fine-tune your model with cleaner, more specific datasets and keep an eye on its outputs regularly to spot anything off. LLMs depend heavily on their training data. Even though LLMs use advanced algorithms to generalize and generate responses, they still rely heavily on the data they were trained on to identify patterns and structures. Think of an LLM as a student who has read millions of books, articles, and forums, but hasn't experienced the real world. If certain topics were missing, biased, or mispresented in the training data, the model's responses will reflect those same gaps. For example, an LLM trained in 2024 won't know about events or discoveries made in 2025 and beyond. As a developer, you need to keep this in mind when using LLMs in dynamic domains like real-time news analysis or evolving technical fields. If your use case requires the latest information, consider supplementing the LLM with real-time APIs, such as web scraping or search tool like SERP API, to bridge the knowledge gap. Another major limitation is token size. Most LLMs have a maximum token limit, also known as a window size or context window, which includes both input and output tokens. For instance, GPT-4o has a token window of 128K. A real-world issue would be processing a long document or providing detailed instructions. If your input exceeds the token limit, the LLM will truncate it, potentially losing crucial context. As a best practice, when dealing with large data inputs, split your content into smaller, meaningful chunks. Libraries like LangChain make it easy to preprocess and manage inputs effectively. Ethics is another critical area. Developers must ask themselves, are you using LLMs responsibly? For instance, using an LLM to impersonate a real person or generate harmful content can lead to serious legal and reputational consequences. Allowing the LLM to generate hate speech, extremist content, or instructions for illegal activities can violate ethical guidelines and may lead to legal repercussions. Always include guardrails in your application, like content moderation filters, or use prompts that set expectations about what the model can and cannot do. Finally, let's talk about the elephant in the room, computational costs. Running state-of-the-art LLMs requires significant hardware resources, which can drive up costs, especially if you are deploying the model at scale. Corporations invest tens of billions of dollars per year in training AI models and building AI data centers. Instead of deploying your own models, you can use AI as a service, which allows you to access powerful AI models and pay only for what you use. This approach eliminates the need for costly infrastructure and maintenance. But if you are building a chatbot or any other app that handles hundreds of requests per second, the cost of API calls can skyrocket. You should optimize your implementation by caching frequent queries, using smaller models for less complex tasks, and batching requests where possible. Let's recap what we've learned. LLMs are powerful tools, but they are not without their flaws. They depend on the quality and scope of their training data, can hallucinate responses, have token and computational limitations, and may introduce bias or ethical concerns if not carefully managed. However, with the right practices like validating outputs, using knowledge grounding techniques, and optimizing your implementation, you can overcome these challenges and build effective, reliable applications. Now that you understand the limitations of LLMs, I challenge you to think critically about how you can design systems that address these issues. What techniques will you use to mitigate bias or ensure accuracy? Drop your thoughts in the Q&A section of the course or shoot me a message on Discord and let's discuss. Hello everyone! Welcome to this presentation on the state of artificial intelligence, present and future, the good and the bad. Imagine a world where machines can think, learn, and solve problems better than humans. That world isn't science fiction, it's happening now. Experts believe that by the end of this decade, AI will surpass human reasoning in many areas. This milestone, called AGI or Artificial General Intelligence, could mark the beginning of singularity where the future becomes unpredictable. AI isn't new. Theories about it emerged in the mid-20th century, but the mainstream revolution began with the development of large language models, or LLMs, in recent years. These models are evaluated based on capabilities like math, language, reasoning, and abstract understanding. The latest OpenAI A1 model was administered an IQ test from Mensa, Norway, and it attained an IQ score of 120. Additionally, the same model achieved a score of 78% on the general physics question answering benchmark, surpassing the average PhD who scored 65. Think about this. You, like any other human on Earth, already have access to one of the best teachers, lawyers, or doctors in your pocket, and often it's free. That's extraordinary progress. Now, let's look at the darker side of AI, what I call the bad. I'll share 3 dystopian scenarios that could become reality if AI isn't managed responsibly. I'll present insights from leading experts in this field. The AI dictator that never dies. The last century has been marked by many cruel dictators. Hitler, Stalin, Ceausescu, and Hugo Chavez, to name a few. Now, a question for you. What did all these dictators have in common? Think of this for 10 seconds. They had in common that they all died. Human life is limited, and for those living under these regimes, that limitation was often their only hope. But what if a dictator never died? Imagine an AI-powered regime that doesn't rely on human leaders, but on algorithms. Imagine an immortal dictator that never sleeps, never tires, and never gives up control. AI could centralize power in the hands of authoritarian regimes, creating systems of mass surveillance that track every citizen in real time, predicting and suppressing dissent before it even forms. Unlike human rulers, an AI dictator doesn't grow old or weak. It learns, adapts, and becomes stronger, embedding itself deeper into society's systems, making resistance nearly impossible. Another challenge is fake news and fake elections. AI can create hyper-realistic deepfakes with video, images, and audio that are indistinguishable from reality. Elections could become illusions with AI-generated propaganda and deepfake campaigns designed to influence each person's belief. In a world where anything can be faked, how can we trust what's real? Think about this. And finally, humans becoming irrelevant. AI is replacing jobs that used to require human intelligence. Careers like programming, engineering, teaching, or legal counseling could eventually disappear. As AI improves, more and more decisions will be made by algorithms instead of people. I'm going to share something that will probably surprise you. Human activities that rely on soft skills, imagination, and creativity like poetry, music, or painting, often referred to as the human touch, are actually the easiest to replace with AI. Why? Because our brain thinks in patterns. Whether it's Vivaldi composing music, Michelangelo creating art, or the best chef in the world designing flavors, they all work by forming patterns of sound, color, or taste that resonate with us. And guess what? That's exactly where AI excels, in deeply understanding and replicating patterns. Let me share a recent scientific study from Nature. It found out that AI-generated poetry is indistinguishable from human-written poetry and is often rated more favorably by leading experts. But the story of AI isn't just about challenges. There's immense opportunity on the horizon. Let's talk about the good, opportunities and innovations. AI is revolutionizing healthcare by detecting diseases like cancer early, accelerating drug discovery, and enabling personalized medicine based on genetic profiles. Just imagine that thanks to AI, in a few years, we'll treat stage 4 cancer just like we treat a cold. Many experts believe that we'll reach what is called longevity escape velocity by the end of this decade. This concept refers to the point where medical advancements extend human life faster than aging progresses. In other words, for every year that passes, medical innovations could add more than 1 year to our lifespan. If achieved, this could dramatically change how we view aging, healthcare, and even the structure of society. Imagine a world where aging is no longer inevitable, but something we can manage and reverse. These advancements make healthcare more accessible, bridging gaps between countries or between urban and rural areas. By automating repetitive tasks, AI frees us to focus on creativity, strategic thinking, and meaningful work. Imagine working shorter hours with higher productivity. Let's talk about robots, the real revolution. AI-powered robots are transforming industries. Tesla's Optimus will likely be introduced in a few years, and as Elon Musk stated, by the end of this decade, there could be more robots than humans. The long-term cost is expected to be comparable to that of a car. Now imagine having a robot at home that works continuously 24/7 for you. It can cook, clean the house, do laundry, walk the dog, garden, and handle almost anything else you can think of. Artificial intelligence is solving humanity's greatest puzzles: climate change, the universe's origins, and quantum mysteries, becoming the ultimate codebreaker of nature, the cosmos, and existence. Let's draw conclusions. AI is no longer a distant dream. It's here transforming our lives. So what are the key takeaways from all of this? We like it or not, the way we live in society are going to change dramatically. AI comes with many promises, but also challenges. AI isn't here to replace us. It's here to augment and amplify what we are capable of. And there's something to really think about. If this presentation hasn't completely captured your imagination, consider this. Right now, these AI models are just getting started. Think of them as the amoeba stage in the evolution of the human species. In just a few years, they are going to grow exponentially. Things are moving at lightning speed. So let's not just sit back and watch it all happen. Let's be part of it. Dive in, explore, and imagine how AI can transform your work and creativity. The future isn't something that's just happening to us. We are shaping it right now. Engage with AI, dream big, and take this opportunity to be part of something extraordinary. Thank you for listening, and remember, we are shaping the future. In this section, we'll dive into how LLMs work and discuss training LLMs. In the context of large language models, an AI model is a type of neural network, specifically a deep neural network, based on the transformer architecture. There are three major stages in training large language models like ChatGPT. Let's start with the first one, creating the pre-training dataset, which means downloading and processing the internet. This is the foundation stage where a base model is trained on a huge and diverse collection of high-quality internet text. The idea is to expose the model to as much useful information as possible so it can learn grammar, facts, reasoning patterns, and more. Now, you might think this involves downloading the entire internet. And you'd be mostly right. But the final dataset used for training is heavily filtered. One good example of this process is the FineWeb dataset. You can check it out here on the Hugging Face hub at huggingface.co. All major companies like OpenAI, Google, and Anthropic use datasets like this to train their models. What's interesting is that even though the internet is massive, the final dataset is only about 44 terabytes and includes around 15 trillion tokens. That might sound huge, but it actually fits on just a few hard drives. So, how do they go from the entire internet to a much smaller, cleaner database? The answer is processing and filtering. Here's how the process works. This is the pre-training data pipeline. The first step is using a data source. Most of the raw data comes from Common Crawl, an organization that's been indexing the web since 2007. As of 2025, it has archived over 250 billion pages by crawling the entire internet regularly. The next step in the pre-training data pipeline is URL filtering. The first step here is removing unwanted websites using blacklists. This includes sites with adult content, spam, malware, shopping, or dating. This helps eliminate low quality or irrelevant material. Web pages are stored as raw HTML, which includes code, navigation bars, and styling. This is the HTML code of this page. The goal here is to extract just the meaningful written content. No HTML or JavaScript code, no menus, just the core text. Then comes language filtering. Language classifiers are used to keep only pages in the target languages. For instance, FineWeb keeps pages that are at least 65% English. This step also allows developers to decide how multilingual the model will be. The next step is deduplicating the data and quality filtering. Duplicate or near duplicate content is removed to avoid repetition. Additional filters target low quality text that could hurt the model's performance. And finally, pages containing personal information like addresses or social security numbers are identified and removed to protect privacy. After all these steps, you are left with a refined, high-quality dataset like FineWeb's 44 terabyte of content, which covers everything from earthquakes facts to general knowledge articles. I took the first pages from FineWeb and put them all here in this text file, and I end it up with this. At this point, all the clean text is concatenated into one long stream and then tokenized. That means it's broken down into small pieces called tokens, which the model can understand and learn from. The model sees all of this data as one massive sequence of tokens. Note that AI models have a knowledge cutoff date because their pre-training data is like a lossy zip file of the internet, filtered, compressed, and outdated, missing the latest updates. For example, the cutoff date for GPT 4.5 that was released in winter 2025 is June 2024. So, in a nutshell, pre-training begins with transforming raw internet content into a dataset, which is then used in the full pre-training process, including tokenization and neural network training, to enable an LLM's language understanding and generation. Also, keep in mind that the performance of a large language model depends heavily on the quality and size of its pre-training dataset. We are now taking a break, and in the next video, we'll go over the next step in training a model, the tokenization of the pre-training data. In the last video, we talked about the first stage of training neural networks, the foundation of large language models, which is called pre-training. This stage involves creating a high-quality, diverse version of the internet by filtering out low-quality data. The end result is something like a giant one-dimensional string of text, stretching from beginning to end. Think of it like a huge file. These are the first few pages from FineWeb. Once the raw data is pre-processed, the second and the next big step is called tokenization. Neural networks, the core of LLMs, work with one-dimensional sequences of discrete symbols. These symbols come from a limited set of possibilities, often referred to as vocabulary. Now, at the lowest level, text is stored on computers as bits, just zeros and ones, using encodings like UTF-8. This is the binary representation of the raw text data we saw earlier, of this data. But feeding such long binary sequences into a neural network is incredibly inefficient. So instead, we need more meaningful symbols to keep the sequence lengths manageable. A basic improvement is to group bits into bytes, which are 8 bits each. This gives us 256 possible values. So the text can be represented as a sequence of bytes, each with a unique ID from 0 to 255. But modern LLMs take this a step further using a technique called byte pair encoding, or BPE, or something very similar. Here's how BPE works at a higher level. It starts with all the bytes in the data. Then it finds the most frequent pair of consecutive symbols. Say the byte for O followed by a space. O followed by a space, and merges them into a new symbol with a new ID. These are all accuracies of O followed by a space. Every time that pair appears in the data, it gets replaced by the new symbol. This process repeats, reducing the length of the sequence while increasing the vocabulary size with each new merge. It continues until the vocabulary reaches a target size, usually around 100,000 symbols. For example, GPT-4 uses a vocabulary of 100,277 symbols. This whole process of turning raw text into these compact numerical representations is called tokenization, and the output symbols are called tokens. These are the tokens for this raw text data. Pre-training datasets are huge, resulting in incredibly long sequences of tokens. The FineWeb dataset, for example, contains around 15 trillion tokens. These tokens are what the model learns from to understand and generate language. If you want to see how tokenization works in practice, check out this tool, Tick Tokenizer. Just pick a model and start typing. For example, learning how LLMs work is broken into 7 tokens. You'll notice how tokens don't always match up one-to-one with words. They are optimized for efficiency. Coming back to the FineWeb dataset, this is the token representation of the first few pages of the data. Just think of these numbers as unique IDs. To wrap up, tokenization is a key step that transforms pre-processed internet text into a format neural networks can learn from. This format is usually a one-dimensional sequence of finite symbols called tokens. Tokenization makes it possible for LLMs to discover patterns, relationships, and meaning across vast amounts of data. We've covered the first 2 steps of training the deep neural network used by the LLM: getting and filtering the raw internet data and transforming it into tokens. In the next video, we'll discuss the next step, which is training the neural network. In this video, we'll explore the third major stage in training large language models, training the neural network. Let's dive in. At the heart of a large language model is a deep neural network based on the transformer architecture with billions of parameters, also referred to as weights. Think of them as numerical settings that determine how the network processes input, sequences of tokens, to produce output, predictions for the next token. LLMs employ complex mathematical expressions that combine input tokens with these parameters to make predictions. Once the internet text has been pre-processed and tokenized into a massive one-dimensional sequence, the next critical step is training the neural network. Training means feeding it a huge amount of tokenized text from the internet and teaching it to predict what comes next, what token at a time. As it goes, the model adjusts its internal settings to get better at spotting patterns and understanding how language flows. This is where the model learns to recognize patterns in language by predicting the next token, and where most of the computation happens. As the model trains, it repeatedly adjusts these parameters to better predict what token should come next. Each prediction is compared against the actual next token in the training data, and the model updates its parameters to reduce the error. This process is called optimization. Over time, by spotting patterns and learning how language typically flows, the model becomes better at generating meaningful, coherent responses. The process begins by taking small windows of tokens from the tokenized dataset. These are sampled fairly randomly. The window size can vary up to limits like 16K, 74K, or 128K tokens, depending on the model architecture. Very long windows are expensive to compute, so practical limits are set. Let's take this example sentence. I enjoy eating pizza with my family on Monday afternoons. And we take a window of 4 tokens. I enjoy eating pizza. These are the tokens for these words. The goal of training is simple. Predict the next token after the context window. This is called next token prediction, and it's the core of how LLMs learn. The 4 input tokens are fed into the neural network. The network outputs a probability for every possible next token in the vocabulary. In GPT-4, that means predicting from 100,277 possible tokens. For example, it might produce on with a probability of 1%, because with a probability of 3%, and with a probability of 2%. So in this case, the network predicts because with the highest probability, but the correct token in our dataset is actually with. Now it's learning from mistakes. Because we know the correct next token, we can compare the network's prediction to the true answer. We then calculate an error and update the neural network's parameters to improve its predictions next time. This process is known as gradient descent. Optionally, if you'd like to dive deeper into the gradient descent algorithm, you can check out this Wikipedia page. So, initially, the network's predictions are mostly random because its parameters, or weights, are randomly initialized. The training setup is called self-supervised learning because the tokens, aka the labels, come directly from the data itself. So, the next time the model sees a similar sequence, it's more likely to assign a higher probability to with, which is the correct answer in this context. This cycle, sampling a window, predicting the next token, comparing to the actual answer, and updating the weights, is repeated millions or even billions of times across the training data. With every update, the model gets a little better at predicting what comes next. Over time, it builds an internal understanding of how language works. To speed up training, this process is done in batches. Many sequences of tokens are processed in parallel using powerful hardware like GPUs and TPUs. This parallelism makes it possible to train models efficiently even on massive datasets. Let me tell you a few words about GPUs and TPUs. A GPU is a graphical processing unit originally built for gaming. But today, it's used for deep learning because it can do millions of tasks at the same time. Great for training models. To give an idea of performance, a high-end NVIDIA GPU based on the Blackwell architecture can perform quadrillions of floating point operations per second. A quadrillion is equal to 1,000 trillion, or 10 to the power of 15. That's why companies like NVIDIA have skyrocketed in value, because they power the AI revolution. A TPU is a tensor processing unit. It's a special chip designed by Google specifically for machine learning. It's even more optimized than a GPU for tasks like matrix multiplication, which LLMs use a lot. This is an example of a Google Cloud TPU data center. So whether it's a GPU or a TPU, the goal is the same: train LLMs faster and more efficiently. Once the model is trained, it can start generating text. That's called inference. The model takes in a starting prompt, which can be a few words or full sentences. The model then looks at that input and guesses what the next word or token should be, based on probabilities. It's kind of like flipping a weighted coin. The more likely a token is, the higher the chance it will get picked. That token gets added to the sequence, and the process repeats until we've got a full response, like this one. So what we covered? During training, a language model learns to predict the next token based on a fixed number of preceding tokens. This number is known as the window size, context window, or sequence length. In essence, training a large language model involves feeding it sequences of tokens and teaching it to predict what comes next. It learns from mistakes by updating its parameters using gradient descent. This cycle is repeated across billions of examples to build a powerful model. And to make this process efficient, it runs in parallel on specialized hardware called GPUs or TPUs. That's the core of how large language models are trained. It's all about tokens, prediction, learning from mistakes, and going it at scale. We are taking a break, and in the next video, we'll go into the next phase, which is post-training. Let's move on and take a look at how language models like ChatGPT go from simply reading the internet to becoming helpful, trustworthy assistants. We'll start this video with what post-training is all about, dive into how it works, and wrap up with why it matters. Note that in the context of LLMs, post-training is commonly referred to as fine-tuning or instruction tuning. So first, the base model is trained using a process called pretraining, where it learns from massive amounts of internet text. The goal here isn't to create an assistant, it's to build a general-purpose model that can predict the next word or token based on context. Also, keep in mind that the base model has a knowledge cutoff date because of the static nature of the internet data included in pre-training. For example, GPT 4.5, released in winter 2025, has a cutoff date of June 2024. And since pre-training is expensive and resource intensive, it's not repeated too often. The pre-training stage is extremely expensive, taking months of compute time, thousands of GPUs, and billions of dollars. And at this point, the model isn't really an assistant. It's more like an internet document simulator. It can generate text that statistically looks like something you'd find online, but it doesn't yet know how to follow instructions or carry on a conversation. That's where post-training, aka fine-tuning, comes in, and it's just as important, even though it's cheaper and much faster. It depends on the model, but to give you a general idea, pre-training takes months to complete, while post-training usually takes just a few hours. The goal of post-training is to transform the base model into a helpful AI assistant, like ChatGPT, one that can answer questions, support multi-turn conversations, and behave in a way that feels human-like. There are two key parts to this process: supervised fine-tuning, or SFT, and reinforcement learning, or RL. Let's start with supervised fine-tuning. This is where we take the base model and continue training it. But now, instead of using internet text, we use structured conversations between humans and assistants. These conversations are created by so-called human labelers, who are contractors which are given detailed instructions by the company developing the model. They are asked to come up with thousands of prompts, and for each prompt, they write the ideal assistant response. Humans don't write everything from scratch. They use an existing LLM to generate questions and answers, and then they edit the answers. Take a look at this document that describes how to train language models to follow instructions with human feedback. The instructions people follow often emphasize three qualities: helpfulness, truthfulness, and harmlessness. The assistant learns by example, adopting the behavior and tone of the responses written by these labelers. Now, this dataset of conversations, called the SFT dataset, covers a wide range of topics and is formatted with clear distinctions between human inputs and assistant outputs. The conversations are tokenized into sequences that the model can learn from using the same algorithm as pre-training, predicting the next token in the sequence. But the key difference is that now it's learning from assistant-style conversations instead of raw web pages. As a result, the model starts picking up the statistical patterns of how an assistant should respond. It learns not just what to say, but how to say it, clear, concise, and aligned with the values defined during training. The outcome? A model that behaves like a helpful assistant, imitating the tone and quality of the human written examples. If you ask it something like, "What are the top 10 mountain peaks in Europe?" and that exact question and response were in its post-training data, it will likely generate the same answer. If not, it will fall back on what it learned during pre-training, blending both sources of knowledge. By the way, you can try different models on the Hugging Face playground. Just create a free account, generate a token under Settings, head to the playground, select the model you want to test, and run queries. Let's select Microsoft 5.4, which is a small, open source, state-of-the-art model developed by Microsoft. And I'm running the same query. Very well. Just play around with all these models. Now, there's a second part to post-training that's gaining more attention: reinforcement learning. Here, the model generates multiple possible responses to a prompt, and human evaluators or even automated systems rank or score those responses based on how well they align with the desired assistant behavior. The model then adjusts itself based on this feedback, learning to prefer better, more helpful responses. This approach is especially useful in complex domains like math or logic, where fine-tuning alone might not be enough. So to recap, post-training is what transforms a raw language model into a helpful assistant. With supervised fine-tuning, it learns from examples of good conversations. Then, through reinforcement learning, it refines its behavior even further. It's not perfect, of course, but the assistant we are chatting with today is the result of that powerful combination of learning steps. Now, it's worth noting that the first two stages, pre-training and supervised fine-tuning, have been around for years, and all major LLM providers use them. But reinforcement learning, or RL, is still a relatively new area. We'll take a quick break now, and in the next video, we'll dive deeper into RL. Let's dive into reinforcement learning in the context of training large language models using the analogy of going to school and working with textbooks. Training LLMs can be seen in three major stages, much like a student progressing through their study. First, there's pre-training, which is akin to reading all the expository material in textbooks across various subjects. During pre-training, the model is exposed to vast amounts of text from the internet, allowing it to build a broad knowledge base and understand the statistical patterns of language. This stage results in a base model, which is essentially an internet document simulator. The second stage is supervised fine-tuning, which is comparable to looking at worked solutions in a textbook provided by a human expert. In SFT, the base model is trained on a curated dataset of conversations between humans and an AI assistant, where human labelers provide the ideal assistant responses to various prompts. The model learns to imitate these expert demonstrations and adopt the persona of a helpful, truthful, and harmless assistant. While SFT is crucial for tuning a base model into an assistant, it essentially relies on imitation of human-provided data. The third and final major stage is reinforcement learning, which is like doing practice problems in a textbook where you are given the problem description and the final answer, but not the step-by-step solution. In this stage, the LLM gets to practice generating responses and refine its behavior based on feedback. The model explores different actions, receives reward signals from its environment, and updates itself to maximize those rewards. Over time, it improves through this feedback loop. It's not pure trial and error, but rather guided optimization based on the outcomes it experiences. Here's how reinforcement learning works for LLMs, drawing on the analogy we used so far. The first step is prompt and candidate solutions. Similar to a practice problem, the LLM is given a prompt, the problem statement. The model then generates multiple different solutions or token sequences in response to this prompt. Because these models are not deterministic, each attempt to solve the same prompt can result in a slightly different sequence of tokens. The next step is feedback and reward. Unlike SFT, supervised fine-tuning, where the model learns from expert-provided solutions, in reinforcement learning, the model receives feedback based on whether its generated solution is correct, achieves the final answer, or desirable according to certain criteria. For verified domains, like math problems where the answer is concrete, for example is 10, the model can be automatically assessed. Solutions that lead to the correct answer are rewarded or encouraged. Finally, learning and improvement. By trying out many different solutions and receiving feedback, the model learns which token sequences are more likely to lead to the desired outcome. It adjusts its internal parameters to favor the successful paths and discourage the unsuccessful ones. This process allows the model to discover its own effective strategies for problem solving, which might even differ from how a human expert would approach it. Reasoning models like OpenAI A1 or O3 have been trained using reinforcement learning. Note that pre-training and supervised fine-tuning have been around for years, and all LLM providers do them. However, reinforcement learning is new and not standard yet. You've got an idea now of how LLMs become so smart. We are taking a quick break, and in the next lecture, we'll dive into something truly transformative, becoming better than humans. AGI and ASI with reinforcement learning. Let's explore how reinforcement learning enables AI systems to surpass human intelligence and what we can learn from AlphaGo's historic success. AlphaGo was a breakthrough in AI. It learned the game of Go not just by studying human games, supervised learning, but more importantly, by playing against itself using reinforcement learning. Through millions of self-play games, AlphaGo explored a vast range of possibilities, constantly refining its strategies based on what led to victory. Let's take a quick look at the PDF Mastering the Game of Go Without Human Knowledge, which explains how AlphaGo was trained. On this chart, you see the two learning strategies, supervised learning in purple and reinforcement learning in blue. The y-axis shows the ELO rating, which measures playing strength, and the x-axis shows training time in hours. With supervised learning, AlphaGo was initially trained by imitating expert human moves, studying thousands of professional games. It reached a high skill level quickly, but notice how the curve flattens. It hits a ceiling just below world champion Lee Sedol. Why does this happen? Because imitation alone can only get you as far as the best human knowledge available. Now, look at reinforcement learning. This is where things get exciting. Instead of just copying, AlphaGo began to play against itself, exploring billions of alternative moves and strategies, many of which humans had never considered. Over time, its ELO rating kept rising, and it surpassed the level of Lee Sedol, becoming stronger than any human ever. So in short, supervised learning was about imitating humans. But reinforcement learning let AlphaGo go beyond humans, finding truly original, superhuman strategies through self-play. One of the most iconic examples of this was Move 37 in its match against world champion Lee Sedol. It was so unconventional that expert commentators thought it was a mistake. Yet it turned out to be a brilliant, game-changing move that no human had ever considered. This highlighted a critical truth. Reinforcement learning allows AI to go beyond human intuition and explore strategies we'd never think of. Let's watch that move for a few seconds.
There was a 1 in 10,000 probability that move 37 would have been played by a human player. So it knew that this was an extremely unlikely move. It went beyond its human guide and it came up with something new and creative and different.
I want to see Lee Sedol when he sees this move.
He's back, Lee is back.
알파고는 기실은 확률적 계산을 하고 그냥 이기기 위한 그런 머신에 불과하다고 생각을 했었는데 그 수를 보는 순간 아니구나. 충분히 알파고도 창의적이다. 정말 아름답고 바둑의 그런 아름다움을 잘 표현해주고 굉장히 창의적인 요소였다.
This move is very special because with this move, all the stone played before is work together. It's connect. It looks like a network, link everywhere. It's very special.
Reinforcement learning isn't just about board games. When applied to LLMs and other AI systems, it gives models the ability to reason, solve complex problems, and improve through trial and error. Instead of just imitating human responses, these models generate different approaches, test them, and learn what works best. This means RL-trained LLMs aren't bound by the limits of human thought. Just like AlphaGo discovered new tactics in Go, LLMs could develop entirely new strategies for reasoning, problem-solving, and decision-making, strategies that go far beyond anything seen in their training data. While reinforcement learning could lead to AGI and beyond. AGI is short from Artificial General Intelligence. The most powerful aspect of reinforcement learning is that it frees AI from purely human imitation. Supervised learning gets you to human-level performance, but reinforcement learning is what enables systems to surpass it. When applied to verifiable domains like math, coding, and logic, reinforcement learning allows AI to optimize for correct answers, pushing it to find faster, smarter, or entirely novel solutions. And if these strategies start to generalize across domains, we inch closer to artificial general intelligence, systems that can learn and reason across a wide range of tasks. Eventually, as RL-driven systems continue to evolve, it's plausible they could develop forms of intelligence that not only rival but exceed human cognition, what we call artificial superintelligence, or ASI. Just like AlphaGo's Move 37, the paths these systems take may be unintuitive, unexpected, and more effective than anything we've imagined. Let's wrap it up. In short, reinforcement learning gives AI the ability to experiment, adapt, and grow beyond human-level thinking. AlphaGo showed us a glimpse of this potential, defeating one of the world's best players by making moves that seemed impossible. Now, as we apply reinforcement learning to powerful models like LLMs, we are beginning to unlock even greater potential, opening the door to a future that AI isn't just learning from us, but outthinking us. Let's dive into reinforcement learning from human feedback, or RLHF, and explore how it compares to standard reinforcement learning, or RL. So here's the idea. Standard reinforcement learning is great when outcomes are easy to verify, like math problems where answers are clearly right or wrong, or games like Go, where you either win or lose. In these cases, defining a clear reward function is straightforward. But what about subjective tasks, like writing a summary, telling a joke, or generating creative content? Here, there's no single correct answer, and creating an automatic reward function that accurately captures human preferences is tough. That's where RLHF comes in. Here's how RLHF typically works. The first step is generate rollouts. Given a prompt like create a joke about cakes, the language model generates several different responses called rollouts. Think of these as multiple drafts or alternative versions. Instead of developing a complicated scoring system, we simply ask humans to rank these responses from best to worst. Ranking is much easier than assigning specific scores, especially for subjective content. We then use this human ranking to train a reward model, which is a neural network that learns to predict human preferences. Essentially, this model acts as a proxy simulating human judgment. The next step is reinforcement learning with the reward model. Once trained, we use the reward model to guide further training of our original language model. Instead of relying directly on human evaluation or fixed objectives, the language model now learns to produce responses that the reward model predicts human will prefer. Now, let's clearly compare RLHF with standard RL. In traditional reinforcement learning, the reward signal is objective, measurable, and clear, like getting the correct answer to a math problem or winning a game. The model learns through trial and error, optimizing for a well-defined outcome. In contrast, RLHF has a subjective reward signal learned from human preferences. The reward comes from the trained reward model, not a fixed goal. The language model thus aligns more closely with what humans like, even without a definitive correct answer. Alright, so let's summarize the advantages and limitations of RLHF. Let's start with what makes RLHF great. First off, it's really good for handling subjective tasks. Think storytelling, summarization, or creative writing. These are areas where traditional reinforcement learning just doesn't work because there's no obvious right answer and no clear reward to go after. It also makes human feedback a lot more practical. Instead of asking people to come up with the best response from scratch, we just ask them to rank a few options. That's way easier and way more scalable. And here's the really cool part. RLHF builds human intuition into the training process. It helps the model learn what people actually prefer, even if we can't always put those preferences into words or rules. But there are definitely some challenges too. The reward model is not perfect. It's just an approximation of what people might like. Sometimes it gets it wrong or misses the subtle stuff. And language models are smart, maybe a little too smart. They can figure out how to game the reward model, generating answers that technically get high scores but aren't actually useful or meaningful. Also, we can't train forever with RLHF. If you go too far, the model might start producing weird, unnatural outputs. So usually, we treat it more like a final tuning step rather than an ongoing training loop. Wrapping it all up, RLHF is a powerful approach for aligning large language models with human judgment, especially for subjective tasks. It relies on human-guided reward models, making reinforcement learning applicable where traditional methods fall short. However, unlike standard reinforcement learning's clear objective goals, RLHF depends on learned reward signals, bringing imprecision and potential exploitation risks. While RLHF marks a significant advancement, it's essential to recognize it isn't a magic bullet. It's more of an intelligent tuning process with practical limitations worth keeping in mind. Let's talk about one of the biggest challenges in large language models, hallucinations. That's when the model gives you a confident answer that sounds good, but is completely made up. It feels right, even helpful, but it's just not true. In this video, I'll break down what hallucinations are, why they happen, and how we can reduce them using smart training techniques, tool integrations, and memory design. So why do hallucinations happen in the first place? To answer that, we need to understand where a language model's knowledge actually comes from. LLMs rely on two types of memory: vague recollection and working memory. Let's start with vague recollection. This refers to the knowledge the model picks up during both pre-training and post-training. In pre-training, it learns general language patterns and facts by processing massive amounts of text. During post-training, it refines this understanding with more specific, focused data, like instructions or human feedback. All of this knowledge gets compressed into the model's internal parameters. It's kind of like long-term memory, but fuzzy, more about patterns than precise facts. Think of it like a blurry, compressed zip file. If a piece of information showed up a lot during training, the model's more likely to remember it well. But if it was rare or nuanced, the memory might be incomplete or just plain wrong. That's when hallucinations pop up. The model fills in the gaps with guesses based on fuzzy or outdated info. Now, compare that to working memory. This is the model's context window. It includes the current conversation, your prompt, the model's responses, and anything else you add, like documents or search results. This memory is short-term but crystal clear. There's no guessing here. If it's in the context window, the model can see it directly. This difference is super important because if we want better accuracy, we either need to help the model realize what it doesn't know or give it access to the right information in real time. One of the simplest and most effective ways to reduce hallucinations? Just teach the model to admit when it's unsure. During training, developers include examples where the model says things like, "I'm sorry, I'm not sure about that," or "I don't have that information." This helps the model learn that it's totally okay to say "I don't know" instead of making something up. some researchers even talk about neurons of uncertainty, parts of the model that activate when it's less confident. By feeding it enough examples of honest, uncertain responses, the model learns to pause instead of hallucinate. Meta's llama models, for example, have used this technique with pretty good results. Another strategy is to give the model tools, especially web search. Let's say the model faces a factual question, but it's not sure if it has the right info. Instead of guessing, it can generate a search query, fetch real-time results, and use that data in its response. That updated info goes straight into the context window, its working memory. So now the model can quote current facts, cite sources, and respond with much better accuracy. This is exactly how search or browsing features work in tools like ChatGPT. The model learns when it knows enough to answer on its own and when it needs to go look something up. Let's ask ChatGPT this. Write a summary about aerodynamic toothbrush 2.0 reloaded. As you can see, it's unsure about the answer and uses the web search tool. It finds out that the product doesn't exist, says no, and even offers some possible variations, just in case the user misspelled it. Now I'm adding to the prompt. Don't use any tool like the web search tool. In this case, ChatGPT will try to generate an answer based solely on its training data, without access to external tools and with only a vague memory of patterns of similar sounding products. It might end up fabricating a description of a non-existing product. So, in summary, to reduce hallucinations in LLMs, we use a layered strategy, teaching the model to admit uncertainty, equipping it with tools like web search, and providing the right context through working memory. These techniques don't eliminate hallucinations entirely, but they make the model more reliable, encouraging it to pause, search, or stay quiet instead of guessing. Understanding these strategies is essential for using LLMs responsibly. At the end of this video, I want to bring to your attention an amazing AI tool that tries to solve the issue of hallucinations, Perplexity, which is an amazing answering engine. It does search and retrieval by searching the web, much like Google, but instead of giving you a list of links, it extracts the most relevant paragraphs from multiple sources. This relevant info is then AI processed by feeding it into an LLM, which analyzes, organizes, and synthesizes the data into a well-structured answer. This way, by grounding the information on reliable sources, hallucinations are avoided. Welcome back. In this video, we are exploring how LLMs such as ChatGPT, Gemini, Claude, or Perplexity use external tools, Internet web search, deep research, and Python interpreter to enhance their abilities. First, let's clarify an essential point. LLMs are stateless and containerized, meaning each interaction is processed independently. They don't inherently remember previous interactions unless context is explicitly provided. Additionally, these models have a knowledge cutoff date, so they can't access information about events or developments occurring after their training period. Some platforms, like ChatGPT, use additional application-level mechanisms, like memory banks, to store conversation summaries and enhance user experience over time. However, this is an application feature and is not intrinsically built into the model. So, how do stateless models access current information? Let's examine internet web search first. When you ask a question requiring recent information, such as current events or product launches, the model uses special tokens like search start and search end to signal an external web search. The application pauses response generation, conducts a search using engines like Google, retrieves relevant information, and integrates it into the model's context window. This updated context helps the model generate accurate and timely responses, often including citations from its sources. Here's a practical example. I will use ChatGPT and the GPT 4.5 model that has a knowledge cutoff of July 2024. And I'm asking, what movie won Best Picture in 2025? Despite the event occurring after its training, the model can accurately answer. It's searching the web. And the answer is Anora. It also included a YouTube video. Next, let's discuss Deep Research, an advanced tool combining thorough internet research with detailed analytical reasoning. Let's do some in-depth research on taking protein powder and creatine for healthy adults who go to the gym a few times a week. I can say that I was personally interested in this and I used the ChatGPT Deep Research feature. It's asking for additional information. Let's answer both type of protein to the first question. The answer to the second question, let's say 40-year-old males. And the answer to the third question, just supplements. Unlike regular web searches, deep search extensively explores multiple sources and applies logical reasoning to compile comprehensive and nuanced responses. However, this in-depth approach requires considerable computational resources, takes longer, often tens of minutes, and typically comes as a premium feature from providers like ChatGPT, Gemini, or Perplexity. I am pausing the recording until it's done. While working on this task, it's displaying the activity and the sources. It's also displaying its reasoning process or chain of thought. It's been more than 5 minutes since it has started the job and it's still working on it. Let's move on and we'll return a bit later. Lastly, we have the Python interpreter tool. While LLMs excel at language understanding, they are less reliable with complex math calculations. This is known as mental arithmetic, meaning that accuracy declines as complexity increases. To address this, LLMs can use external tools like Python interpreters. Here's how the Python interpreter works. The model emits special tokens signaling the application to execute Python code externally. Once the code runs, the accurate results are returned to the model, enabling precise mathematical answers. Consider this fairly complex math calculation. The LLM alone may produce inconsistent or incorrect answers. You can see how it called the Python interpreter, generated the code for the given expression, and displayed the result. Note that these LLMs are not deterministic, so you can get a completely different answer. If it's not using the Python interpreter tool automatically, you can add to the prompt, use the Python interpreter tool. Like this. Let's return to the deep research task. It's still working on it. We can see the activity and the sources. It will probably be ready shortly. Anyway, I'm not waiting for it anymore. So to summarize, depending on the context, the LLM can start and use external tools. Internet web search equips LLMs with real-time current information. Deep search offers detailed analytical insights, but at a higher resource cost. And the Python interpreter allows LLMs to handle precise computations reliably. Understanding and mastering these tools enables you to fully utilize AI's capabilities, ensuring your workflow remains precise, current, and insightful. Stay tuned for our next video, where we'll give a core summary of how LLMs work under the hood and what we've learned in this section. Thanks for watching. Alright, let's look back to where we started and quickly review the big ideas behind how large language models, or LLMs, actually work. So, what's happening under the hood when you type something into ChatGPT, like create a concise travel guide for visiting Venice, and hit enter? First, your query is tokenized, meaning it's broken into smaller pieces called tokens. These tokens become part of one-dimensional sequence within a conversational protocol, which defines who is saying what. The model gives us a response based on this structure and its training. If I go to tokenizer.versal.app and I paste the query in the user field, here you can see the conversation protocol and the one-dimensional token sequence. The interaction follows a specific format that includes special tokens to mark the beginning and end of user messages and assistant responses. This structure helps the model understand the flow of the conversation. Now, if I take the assistant response and paste it in the assistant field, my entire interaction is represented by 345 tokens. These are the tokens. Each token has a unique ID number from the model's vocabulary, which can contain around 100,000 different tokens. As you continue chatting, asking more questions and getting answers, more tokens representing your query and the model's response are added to this sequence. This growing sequence fits within the model's context window, which acts like the model's short-term memory. Anything inside this window is directly accessible to the model when generating the next response. The size of the window is limited, so eventually older parts of the conversation might fall out of view. And when you click New Chat, that completely wipes the state clean. It's starting from scratch. The context window is emptied and you can start a fresh conversation with no memory of the previous one. This is important because keeping too many old tokens can use up resources and potentially confuse the model if they aren't relevant anymore. So, I encourage you to start a new chat whenever you switch topics, as it helps the model respond faster and more accurately. Now, the big question. Where does the model get the content for its answer? How does it generate those response tokens? The model takes its knowledge from its training, which generally happens in 3 major stages: pre-training, supervised fine-tuning, and the reinforcement learning, often with human feedback. Pre-training is the longest and the most resource-intensive phase. The model is fed the entire internet, previously processed and filtered, so data is high quality, diverse, and relevant. The deep neural network under the hood learns by constantly predicting the next token in a sequence based on the token it has already seen. You can think of the result like a lossy zip file of the internet, represented by billions of numbers. These are the model parameters. This so-called lossy file is a compressed representation, but lossy means it's not perfect. It captures statistical patterns and general knowledge, but not every single detail. Think of it like having a vague recollection of everything it read. After pre-training, we have a base model, which is like an internet simulator, but not yet a helpful assistant. To turn the base model into a useful assistant, it undergoes SFT. Here, it's trained on a curated dataset of example conversations. Human labelers create prompts and demonstrate ideal assistant responses: helpful, truthful, and harmless. The model learns to imitate these examples, essentially getting its personality and conversational skills programmed in. Think of its responses now as simulating what those human labelers would say. Reinforcement learning, often with human feedback, is the final major training stage. This stage further refines the model's behavior. The goal is to encourage the model to generate responses that are not just plausible, but also high quality, aligned with human preferences, and better at complex tasks like reasoning. For tasks with clear right or wrong answers, like math, the model can be rewarded for getting the correct solution. For more subjective tasks, like writing quality, human feedback comes in. Humans rate different model responses, and this feedback is used to train a separate reward model. This reward model then acts as a guide during reinforcement learning, rewarding the main LLM for generating outputs that humans are more likely to prefer. Unlike supervised fine-tuning, which is about imitation, reinforcement learning allows the model to explore and discover better ways to respond, sometimes even finding strategies not explicitly shown in the SFT examples. Reasoning models like OpenAI O1 or O3 use reinforcement learning to optimize their reasoning processes. You should use reasoning models only for difficult problems requiring significant cognitive effort like math problems or coding. So, putting it all together, when you interact with the model, you are talking to something that has learned statistical patterns from vast amounts of text, pre-training, has been taught how to act like a helpful assistant through examples, SFT, and has potentially been further refined using reinforcement learning to improve its reasoning and alignment with what humans find useful. This is reinforcement learning or reinforcement learning from human feedback. It's crucial to remember that each response is generated based only on the tokens currently in the context window. The model is stateless and doesn't inherently remember past checks unless that information is still present within that window. Now, you might know that some versions of ChatGPT have an optional memory feature. This is an extra layer added by OpenAI. If you turn it on, it allows ChatGPT to remember specific things you tell it across different chats, like your preferences or facts about you. However, this memory feature is separate from the core LLM's stateless processing. Even with memory enabled, the model still generates each response based on the context window at that moment, and the memory feature just injects relevant remembered information into that context window. So, in summary, you are interacting with a model that learned from a compressed, imperfect snapshot of the internet, was trained to act like a helpful assistant through supervised examples, and became more sophisticated through reinforcement learning that rewards good behavior. Welcome back. In this video, we'll explore how to authenticate with the OpenAI API, which relies on API keys for access. To get an API key, sign up for a new account at platform.openai.com. Add your billing information and fund your account. Once logged in, click Dashboard and create a new secret key. Save it to a secure place. Improper handling of these keys can expose sensitive information, leading to security risks. This is why secure practices are essential, especially when working with cutting-edge technologies like generative AI. We'll explore two approaches, one quick and simple but not secure, and another that's secure and recommended for real-world applications. Let's get started. First, let's look at a quick, straightforward way to authenticate using an API key directly in your code. This method is suitable for quick tasks, but should never be used in production. Here's an example. I am pasting the code that uses the OpenAI API and makes a request to a GPT model. For now, don't focus on the code itself, just on the authentication process. We'll discuss the code in detail in the next video. This code uses the OpenAI API library, which isn't part of Python's standard library. To install it, simply run pip install OpenAI -q. Run the command in the terminal or in a Jupyter Notebook cell. If it's already installed, you can upgrade it to the latest version by running pip install --upgrade OpenAI -q. And if you want to display your version, run pip show OpenAI. This is the current version. Let's return to authentication. I defined a variable that holds the OpenAI API key. To perform authentication successfully, the API key client option must be set either by passing the API key directly to the client, line number 4, or by setting the OpenAI API key environment variable. In this example, I'm defining an OpenAI client, which is an instance of the OpenAI class, and passing the API key as an argument. I'm running the code. It will write a poem about a lonely robot exploring a futuristic city. Very nice, I've got the poem written by GPT-4o. In this example, I pass the API key directly to the OpenAI client. The client authenticates and sends a request. The model generates a response, such as a creative poem. However, saving API keys directly in your code is a bad practice. If this file is shared or uploaded to a version control like GitHub, your API key is exposed. Now, let's implement a secure and professional approach using the Python.env library. This library allows you to store sensitive information like API keys in a .env file, keeping your credentials safe. First off, install python.env. Run pip install in your terminal or in a Jupyter Notebook cell. Pip install python-.env -q. X installing the library. Next, using a text editor, create a file in your project directory and name it .env. I'm saving the file as .env in the projects directory. Add the following line: OpenAI API key equals, and the key in double quotes. I'm copy-pasting the key. On Linux or macOS, files starting with a dot are hidden by default. Adjust your File Explorer settings to make them visible. For projects using multiple keys from OpenAI, Pinecone, or Google Gemini, include all in the same .env file. I'm saving the file. Here's the Python code to securely load and use the API key. From .env, I'm importing two functions, load.env and find.env. Load.env reads variables from the .env file, and the find.env returns the path to .env in the current directory. Override equals true is necessary if you want to change anything in .env. I am running the code. If you want to retrieve the API key, import OS and call os.getEnv and the name of the variable, OpenAI API key. I'm commenting the line that defines the API key in the code and also removing the API key argument from the OpenAI constructor. And I'm running the code. Now it authenticates to OpenAI using the key saved in the environment variable from .env. Let's talk about best practices and common pitfalls. Never share your .env file. This is the .env file from the project's directory. Add it to your .gitignore file to prevent accidental uploads to repositories. Use environment variables for all sensitive credentials. This includes keys for OpenAI, Gemini, Anthropic, Pinecone, LangChain, Hugging Face, and others. And rotate API keys periodically. In case of a security breach, rotate your keys immediately. In this video, we learned two methods for authenticating to the OpenAI API, The first method using an API key directly in your code, which is quick but insecure, and the second method using Python.env, which is secure, scalable, and best practice for real-world applications. Always prioritize security when working with sensitive data like API keys. In the next video, we'll dive deeper into making API requests and handling responses with the OpenAI API. See you there. Hey everyone, welcome back. In this lecture, we are diving into something incredibly exciting: how to make your first GPT API request. By mastering this, you can harness GPT's capabilities to generate text, write code, or even compose poetry. Think of this as your gateway to building intelligent applications. Let's jump right in. Let's start fresh and go step by step. Make sure you've already set up your API key using Python.env as we covered in the last video. First, we start by importing the OpenAI class from the OpenAI library. This library lets us interact with OpenAI's API, which includes GPT models. Next, we create an instance of the OpenAI client. Client equals, and I'm calling the class constructor. Think of this as establishing a connection to OpenAI's platform, so you can send requests and receive responses. Now, we are using the client to create a chat completion by calling client.chat.completions.create. This is where the magic happens. We are asking OpenAI's GPT model to generate a response based on the input or prompt we provide. This method returns a completion or response object. So response equals. When calling this method, we'll use keyword arguments. This means we specify the name of the argument followed by an equals sign and then its value. This way, we don't have to worry about the order of the arguments. The first argument is the model, and it should be one of the available OpenAI models. Check the output of client.models.list to see all available models. I'm using a for loop for model in client.models.list print model, and I am running the code. Of course, I need to run the code that defines the client. I am commenting out this code because it's not done, and I'm running the code in this cell. In the next cell again, I'm uncommenting this code. Very well. These are all available models. Also check the models on OpenAI's website for more details about available models. We'll use GPT-4o Mini, which is a small, affordable, and efficient multimodal model designed for fast, lightweight tasks. The next argument is messages, which is a list of dictionaries. Each dictionary or message in the list has two properties: role and content. The role can take one of three values: developer, user, or assistant. Each role has a content field which contains the text or value for that role. Conversations can be as short as one message or can span many exchanges. Typically, a conversation is formatted with a developer message first, followed by a user message. Messages with the developer role provide instructions to the model that are prioritized ahead of user messages. This acts like instructions for the AI, defining its behavior or persona. Here, we are telling it to act as a sci-fi writer and poet. This message role, developer, used to be called the system prompt, and it was renamed to developer in the latest versions of the API. Next, we have a user message, which is the prompt or what we ask the assistant. In this case, we are asking the AI to write a poem about a lonely robot exploring a futuristic city. Next, I'm setting the temperature. Temperature equals 1. The temperature parameter controls the randomness of the output. A value of 1 means the AI will produce more creative and diverse responses, great for writing poems. Finally, we print the generated content. Print response dot choice of 0 dot message dot content. The response is stored in the choices list, and we're accessing the first choice. Then its message content. I am running the code. This is the poem written by GPT-4o Mini based on our input. Okay, we are done for now. In this video, you've learned how to make API calls to OpenAI using the recommended models for generating natural language or code. Before we wrap up, here's one last remark. This is an extremely fast-moving space, and minor changes may happen in the future. I recommend checking the official documentation to stay up to date. You can find the latest version of the docs here at this URL. In the next lecture, we'll dive into the developer message, which sets the behavior of the assistant. I'll see you soon. Hey everyone, welcome back. In this video, we are diving into a versatile feature in the Chat Completions API, the developer message. By the end of this video, you'll know how to use it to set the behavior of your assistant and completely transform how the model responds to your prompts. The developer message is like setting the personality or rules for your assistant. Whether you want an AI that explains complex concepts step by step, replies concisely, or even talks like Master Yoda from Star Wars, this is the feature that makes it possible. This message role used to be called the system prompt, but it has been renamed to more accurately describe its place in the instruction following hierarchy. Without the developer message, the model defaults to general responses. But by adding a developer message, you can customize the tone, depth, or style of the responses, making it perfect for applications like chatbots, learning tools, or creative assistants. Let's look at how this works step by step. Here's a basic example. The user asks for an explanation of object-oriented programming, and the model responds in the standard general way. I am running the code. There are no errors, but there's no customization either. Let's improve this by adding a developer message. This allows us to give specific instructions about how the assistant should behave. I'm defining a variable for the developer message. You explain concepts in depth using simple terms, and you give examples to help people learn. At the end of each explanation, you ask a question to check for understanding. I'm adding a new dictionary for the developer message. Role colon developer and the content colon developer message, the variable we've just defined. I am running the code. Here, we've defined the developer message. The response now includes a detailed explanation, a simple example, and ends with a question. Can you explain the difference between a class and an object with an example? You can experiment with different behaviors by tweaking the developer message. For example, developer message equals you are a concise assistant. You reply briefly with no elaboration. And I'm running the code. The assistant now responds briefly. This is the entire response. Let's have some fun. You can use the developer message to make the assistant adopt a unique personality. Now you reply in the style of Yoda character from Star Wars. Okay, the response is funny, isn't it? Yes, much to learn there is. A best practice is always to use a developer message for critical applications where behavior consistency is important. Thanks, Rob. Today, you learned about the developer message, how it customizes the assistant's behavior and makes your applications more powerful and engaging. In the next video, we'll explore streaming API responses. See you there. Hello, and welcome to this video on streaming responses from the OpenAI API, a vital concept for Python developers working on generative AI applications. By the end of this lesson, you'll understand how to incorporate streaming into your projects for a better user experience. Let's get started. Imagine interacting with a chatbot that responds as if it's typing in real time. It feels dynamic, engaging, and human-like. That's the power of streaming. Without it, users are left waiting for the entire response, making the application feel slow or clunky. Streaming allows your application to receive partial results from the OpenAI API as they are generated. This is implemented using server-sent events, or SSE, a protocol that pushes updates from the server to the client. With the OpenAI Python library, streaming is as simple as setting the stream equals true parameter. Let's move to coding and see how it works. We are starting with this boilerplate. It's a classical example of code that doesn't use streaming. I'm running it, and you can see how it delivers the entire response at once. I'm still waiting. It delivered the entire response at once. To enable streaming, add the stream equals true parameter to the create method. Stream equals true. Since the response is no longer delivered all at once, we can't display it by printing response.choices of 0.message.content anymore. Instead, we'll process chunks using a for loop that retrieves the partial output. Additionally, I'll rename the object returned by client.chat.completions.create from response to stream. So stream equals and I'm processing the streaming response. For chunk in stream, colon, each chunk contains a delta object which holds the generated text in content. So, if chunk dot choices of 0 dot delta dot content is not none, I'm printing chunk dot choices of 0 dot delta dot content, and the end equals empty string. Using end equals empty string, the print function outputs the content without adding a new line, creating a seamless typing effect. Not every chunk contains content, which is why I'm checking if chunk.choices of 0.delta.content is not none before processing. I'm also displaying a message for the user. AI is typing. I'm running the code. This creates a more engaging experience. In this lesson, we covered what streaming is, why it's important, and how to use the OpenAI client to stream responses from the Chat Completions API. Streaming responses can transform your AI-powered apps, making them faster, more interactive, and user-friendly. Go ahead and try this out in your own projects. And as always, happy coding! Thank you for watching, and I'll see you in the next lesson. Hey guys, welcome back. Now let's move on and see how to include both text and images as inputs. From IPython.display, I'm importing the image class and the display function. If you don't have the IPython library installed, install it by running pip install IPython. I'm defining a variable for the image path. Image path equals images and the triangle 1.jpg. I will preview the image for context. Display of image path. I'm running the code. This is the image. It's a triangle. I drew it myself on a piece of paper. GPT-4o expects images encoded using base 64. To provide images to GPT-4o as base 64 encoded content blocks, follow these steps. First, import the base 64 module. Next, I'll define a function to encode the image. This function will return the image as a base 64 encoded object. df encode image. I'm creating a function because I'll reuse this code in other examples. The function will have a parameter image path. I'm opening the image file and encoding it as a base 64 string. With open of image path and RB, I'm opening the image in read and binary mode as image file. Inside the with block, I'm reading the entire contents of the image as raw binary data and store it in a variable. Image binary data equals image file.read. Lastly, I'll encode the raw image data using base 64. Base 64 turns the binary data into a text string. and the decode UTF-8 part decodes the base 64 bytes object into a string that can be used by GPT-4 Omni. And I'm returning it. Very well. I am testing the function base 64 image equals encode image of image path. I'm defining the system message. System message equals you are a math tutor. And the prompt. What is the perimeter of this triangle? I am making the API call response equals client.chat.completions.create of model equals model, the variable we have defined previously, and messages, which is a list of dictionaries. I am pasting the code to save time. The first dictionary in the list defines the system role, and the second dictionary, the user role. And the corresponding content will be a list. The list consists of the text prompt and the image encoded as a base 64 object. In this example, the image is of type JPEG. Next, the temperature will be 0. I will cut and paste this code in another cell. I want the function in its own cell. I'm running all the code. It's making the API call and I am printing the response. Print response dot choices of 0 dot message dot content. Very well. It understood the image perfectly and calculated the perimeter. The perimeter of the triangle is 32 units. 12 plus 12 plus 8 equals 32. Let's change the image to this one. Now the prompt, the user's question, is written on the image. Let's see if it can understand this. The new prompt will be solve this problem. In this example, the prompt is written on the image. I'm running the code. Now I want the area. Very well, it understood the handwriting perfectly. That's it for now. In this video, you learned how to give GPT-4o local images as input. In the next video, I will show you how to use online images. Let's move on and see how to use online images as input for GPT-4o. I am defining the system message and the prompt. The system message is you respond in English and then translate your response into Japanese. And the prompt will be write a short and concise description of this image. We'll use this image showing astronaut Buzz Aldrin standing on the lunar surface during the Apollo 11 mission in 1969. I'm defining a variable for the image URL. I am making the API call response equals client.chat.completions.create. I will copy and paste the method's arguments from the last example. from this one. Here, instead of using a base 64 encoded image, I'll use the image URL. URL:image URL. And that's it. Finally, I am printing the response. And I am running the code. It is running. Very well. It responded with a description of the image and its Japanese translation. That's it for now. You've learned how to use Python API with GPT-4 Omni, the new flagship model from OpenAI that can reason across different modalities. Feel free to integrate these capabilities into your Python applications to take them to the next level. In this video, we'll go over Chat Completion's API parameters. When you make an API call, besides the prompt, you can send many other parameters so that you can influence the output of the model. You can test these parameters in the OpenAI playground here, or you can make API calls and see the output. These are the parameters that you can change: temperature, maximum length, stop sequences, top P, frequency penalty, presence penalty, and so on. We'll talk more about the OpenAI playground in another video. You are now learning how to develop apps using OpenAI API with Python, so let's see some code. The first important parameter that can be sent to the OpenAI backend in the client.chat.completions.create method is temperature. The temperature is a parameter that controls how creative and random the model is. OpenAI models are non-deterministic, meaning that identical inputs can produce different outputs. A higher temperature will make the model more creative and likely to generate more diverse results, while a lower temperature will make the model more deterministic and likely to generate predictable results. The temperature can be set between 0 and 2, and the default value is 1. If you set it to 0, the model outputs will be mostly deterministic, and if you increase it, the output will be more diverse, but with a higher probability of hallucination. The rule of thumb is that you'll use a lower temperature when there are just a few answers, or even a single one, when you want to generate ideas or a complete story. Think of it as a creative setting of the model. Let's set the temperature very low to 0.1. Now it will give me the most probable answer, and if I run it many times, I'll probably get the same or a similar answer. Note that even if you set a temperature of 0, there's still some randomness in the answer. I'm running the code. And I've got a good answer, which is probably the correct one, but without anything creative in it. If I set the temperature to a higher value, let's say 1, or even higher, it will be more creative. The answer will vary with each call, but the model can also hallucinate. I'm changing the prompt to give me a few tips to grow my YouTube channel. And I'm setting the temperature to 1.8. The temperature is high, and the answer will be more creative. However, note that it can also contain nonsense. The temperature is very high, and there's a lot of nonsense. I'm setting it to 1 and running the code again. Now I'll get a better answer. Also, note that the latest model updates offer something called predictable outputs. The API provides some control towards deterministic outputs by giving you access to the seed parameter and the system fingerprint response field. To receive mostly deterministic outputs across API calls, you can set the seed parameter to any integer of your choice and use the same value across requests you'd like deterministic outputs for. Ensure that all other parameters, like prompt and temperature, are the same across requests. I'm adding seed equals 1234 and changing the model to the latest GPT-4 Turbo. At this moment, GPT-4 Turbo can be accessed as GPT-4-1106-preview. You can get a list of available models by calling client.models.list. I'm running the code. Note that at this moment, GPT-4 is available only to paid accounts. I've got the answer, and if I run the code again, with the same prompt, seed, and parameters, I'll get the same answer. However, because determinism is not 100% guaranteed, you can keep track of any changes in the output by checking the system fingerprint field in the response object. I'm printing the response object. This is the system fingerprint. If system fingerprint is different across API calls, you may get different outputs, mostly due to changes made on OpenAI systems. Let's move on and see other chat completions API parameters. Top P, aka nucleus sampling, is an alternative to temperature, and it controls how much the model focuses on the most likely completions. Its default value is 1, and if you set it to another value, let's say 0.2, it means that only the tokens comprising the top 20% probability mass are taken into consideration. So 1 means use all tokens in the vocabulary, or 100% of the tokens, while 0.2 means use only the 20% most common tokens. It's generally recommended to use either top P or temperature, but not both. Let's change back the model to GPT 3.5 Turbo and set top P to 0.1. I'm commenting the temperature. And I'm changing the prompt to write one sentence review of 1984 by George Orwell. By the way, this is one of my favorite books. I'm running it. I've got the answer, which contains the top 10% most probable tokens. Another useful parameter is max tokens. This is the maximum number of tokens to generate in the chat completion. The total length of the input and generated tokens is limited by the model's context length, and each model has such a context length. Note that there are versions of GPT 3.5 Turbo, GPT-4, and GPT-4 Turbo with a context length between around 4K tokens for the older GPT 3.5 Turbo models and 128 tokens for the newest GPT-4 Turbo model. You can set it to an arbitrary number to limit the response to a certain length. Note that this may cause issues if you set the max tokens value too low, since the output will be cut off and the result will not make sense to the users. I'm setting max tokens to 10 and I'm making the request again. And you see how the answer was cut off to 10 tokens. N is another parameter and indicates how many chat completion choices to be generated for each input prompt. By default, it is set to 1, which means it will give only one answer. This is essentially the same thing as running the same prompt multiple times. I am changing the prompt to write a motto for an ice cream shop. The temperature will be 1.5 because I wanted to be very creative. I'm commenting tab P and setting N to 2. I want 2 completions or 2 answers. I'm running the code. Okay, this is the first answer and this is the second answer. It's in the choices list at index 1. Let's go ahead and talk about the stop sequence. This is another parameter used to make the model stop at a desired point, such as the end of a sentence or a list. For example, if you want single-line completions, you'll use \n as the stop sequence. \n is the return key. I'm changing the prompt to write an article about AI. And I'm running the code. Good. Now, I'm adding stop equals \n and I'm running it again. And I've got a single line of code. Let's see another example. I'll instruct the model to generate an SQL select query for me and I'll use the semicolon for the stop option. This means that the response will end after the query because each SQL query ends with a semicolon. Right? An example of a select SQL query. First, I'm making the API call without the stop parameter. It generated a random query and it also gave some information about it. I'm adding stop equals semicolon and I'm running the code again. We notice how it stopped at the end of the query before the semicolon, which is the stop sequence. You can use up to 4 stop sequences, and in that case, you'll use a list, like this. The first stop sequence, the second, the third, and so on. Let's go over the last parameters, frequency and presence penalties. Frequency penalty is by default 0 and can be set between -2 and +2. Positive values penalize new tokens if they already exist in the text generated so far. The higher the value, the lower the probability of the model repeating the same phrases or words. I want the AI model to write an article about coffee because everybody loves coffee. I'm changing the prompt to write a short article about coffee. I'm running it. This is an article generated with a frequency penalty of 0, the default. If I increase the value, I'll suppress repetition or the model's likelihood to repeat itself. However, this can degrade the quality of the samples. I'm setting it to 1. Now, the probability of repeating words is much lower. But if I set it to a negative value, it's more probable to start repeating itself. If you set it too low, it can even give gibberish by repeating the words. I'm setting it to -1 and running the script. I've got the response, and there's a lot of gibberish, a lot of nonsense. The frequency penalty is too low, and it doesn't have enough words to create the article. The last parameter, presence penalty, is similar to frequency penalty. Same as frequency penalty, it is by default 0 and can be set between -2 and +2. Presence penalty is a parameter that encourages the model to use a diverse range of words in the text it generates. It's like telling the model, hey, don't just focus on the most common words. Use other words in the dictionary too. Positive values penalize new tokens based on whether they appear in the text so far, increasing the model's likelihood of talking about new topics. Okay, I think that's enough, and what you should do now is play around with all these parameters and experience how the model reacts to changes. Hi there! In this video, we are diving into reasoning models, a groundbreaking advancement in generative AI and large language models. By the end of this video, you'll understand how to use reasoning models in Python, manage their context window, and control costs effectively. Let's get started. Reasoning models are the next big leap in AI, and providers like OpenAI, Gemini, Anthropic, and DeepSeek are all racing to develop them. They are particularly powerful for coding, scientific reasoning, and multi-step planning, skills that are essential for building intelligent systems. Think about AlphaFold, the AI that revolutionized protein folding. It didn't just guess the structure. It reasoned through the possibilities. Reasoning models work similarly. This allows them to tackle problems that were previously behind the reach of standard LLMs. What are reasoning models? Reasoning models like OpenAI O1 and O3 are trained to think before they answer. Instead of generating a response immediately, they produce internal reasoning tokens which serve as a form of structured thought. These tokens help break down the problem before formulating an answer. This makes reasoning models ideal for coding tasks, complex queries, and multi-step logic, especially in areas like AI agents, automation, and scientific research. Let's see how to use OpenAI's O3 in Python via the OpenAI API. I've already imported the code needed for authentication. I am pasting a piece of code and we'll discuss it in detail. Reasoning models can be used through the chat completions endpoint like other traditional models. Let's break this down. This piece of code should look familiar. We've used it many times before. However, the task is quite complex. It involves reading from a file, parsing structured log entries, counting occurrences, and then outputting the results. I wanted to create a pretty complex bash script. The key here is the reasoning effort parameter. We can set it to low, medium, or high. High tells the model to do more thinking, which is great for complex problems, but can take longer and cost more. Low is faster and cheaper, but might not be sufficient for intricate tasks. The default is medium. I am running the code. Notice that it takes longer than traditional models. The response will contain a bash script, a well-structured script, with the model reasoning through the logic before outputting an answer. This is the bash script. It also tells us how it works. Very well. Let's move on and talk about managing token usage and costs. Take a look at this image on the OpenAI website. Unlike traditional models, reasoning models generate reasoning tokens alongside input and output tokens. These tokens enable the model to analyze the prompt, explore multiple approaches, and refine its response before producing the final answer as visible completion tokens. Once the response is generated, reasoning tokens are discarded. Now I'll tell you something important. While reasoning tokens are not visible via the API, they still occupy space in the model's context window and are billed as output tokens. So, it's important to monitor token consumption. In a Jupyter Notebook, run response.usage. Each response includes a usage object detailing input tokens, reasoning tokens, and output tokens. For example, this task needed 640 tokens. To limit total tokens generated, including reasoning tokens, set max completion tokens. I'm adding this parameter. Max completion tokens equals, let's say, 10,000. This ensures the model doesn't generate more than 10,000 tokens, even if reasoning tokens take up extra space. Since reasoning tokens are not visible but still consume space, OpenAI recommends reserving at least 25,000 tokens in the context window for best performance. Okay, at the end of this video, let's discuss best practices and common pitfalls. Use reasoning models for complex tasks. They shine in coding, multi-step planning, and scientific applications. Balance reasoning effort for performance. Set reasoning effort to medium as a good starting point, and adjust based on the task. And monitor token usage. Reasoning tokens count toward billing but are not visible in output. And avoid reasoning models for simple lookups. If you need a quick factual response, standard GPT models are more efficient. That's a wrap. In this video, we explored OpenAI's reasoning models. You've learned how reasoning models differ from traditional LLMs, how to use the O3 model for coding tasks, how to adjust reasoning effort for better responses, and how to optimize token usage to manage costs effectively. Now, you are ready to experiment with reasoning models in AI-driven projects. Try them out and see how they enhance complex problem solving in your applications. We are taking a quick break, and in the next video, we'll discuss prompt engineering techniques for reasoning models in GenAI. In this lesson, we'll explore how to craft effective prompts for reasoning models like OpenAI's O1 and O3. If you've worked with traditional LLMs, you may have used structured prompts with chain-of-thought reasoning. But with reasoning models, the approach is different. These models already think step by step internally, meaning some traditional prompt engineering techniques won't be as effective. By the end of this video, you'll know how to optimize your prompts to get the most accurate and cost-effective responses. Here are the key strategies for effective prompting. Use developer messages instead of system messages. The latest OpenAI API no longer uses system messages. Instead, use developer messages for initial instructions. This aligns with how the models process commands internally. For our example, we could use this developer message. I'm adding two messages, role developer and content. You are an experienced Bash developer and provide the complete Bash script as your solution. I'm running it again. Another good prompting technique is to keep prompts simple and direct. Reasoning models excel at understanding clear, concise language. For example, this prompt summarize this research paper in one paragraph is preferable to this one. This is too complex. Another technique is to avoid chain-of-thought prompts. Unlike older models, reasoning models already generate internal thought processes. Adding think step by step may actually degrade performance. Instead, ask for the final outcome directly. Next, use delimiters for clarity. When providing multi-part instructions, use delimiters such as Markdown for code blocks, XML tags for structured data, and the section titles to separate different parts of the input. Start with zero shot, then use few shot if needed. Unlike previous models, reasoning models work well with zero shot prompts, which means that no examples are provided. If the model struggles, provide one or two carefully chosen examples, ensuring they align exactly with your instructions. This is an example of a well-structured few-shot prompt. Provide specific guidelines. If you need constraints, explicitly state them. For example, instead of suggest a cost-effective AI solution, use suggest an AI solution with a budget under 500 and a setup time under 2 hours. Be clear about your end goal. Tell the model what a successful response looks like. Encourage the model to keep reasoning and iterating until it matches your success criteria. This is an example of a prompt. Generate a project plan for an AI-powered chatbot, and the success criteria would be the plan must outline data sources, model selection, and deployment. Keep the cost under $1,000 per month. Okay, let's draw a conclusion. To get the best results from reasoning models, use a developer message, keep prompts clear, concise, and well-structured. Start simple, avoid unnecessary step-by-step instructions, and use delimiters when handling complex inputs. Remember, these models are built to reason internally. Your job is to guide them efficiently, not micromanage their thought process. That's it for this video. Thank you. Welcome back. In this video, we'll cover the Whisper model, which is a speech recognition one. By the end of this video, you'll be able to transcribe audio into whatever language it is and translate the transcription into English. This is really cool, so stay with me. Whisper is a trained open source neural network that approaches human-like robustness and accuracy on English speech recognition. The model supports tens of languages and was trained on hundreds of thousands of multilingual and multitask supervised data collected from the internet. The OpenAI API provides two endpoints, transcriptions and translations, based on the state-of-art open-source Whisper model. Practically, you can use this model to transcribe audio into whatever language the audio is in, or to translate and transcribe the audio into English. I'm importing OS and loading the API key as an environment variable. I'm also importing the OpenAI class. So from OpenAI, import the OpenAI class. And I'm instantiating a client object. Client equals OpenAI. I'm calling the constructor of the class. In this example, I'll use Whisper to create the transcript of an audio file. I'll use a small part of President Ronald Reagan's speech to the people of West Berlin from July 12, 1987. It's the famous Tear Down This Wall speech. This is the audio file, rr.mp3, and this is the original transcript. I will play the file. There are just a few phrases, so let's listen to the audio so that we can compare to what Whisper will do. This part is 1 minute, 30 seconds long, and you can fast forward if you don't want to listen to it entirely.
We welcome change and openness, for we believe that freedom and security go together, that the advance of human liberty can only strengthen the cause of world peace. There is one sign the Soviets can make that would be unmistakable, that would advance dramatically the cause of freedom and peace. General Secretary Gorbachev, if you seek peace, if you seek prosperity for the Soviet Union and Eastern Europe, if you seek liberalization, come here to this gate. Mr. Gorbachev, open this gate. Mr. Gorbachev, tear down this wall.
That was the audio, so let's put Whisper to work. I am opening the file, the audio file, in binary mode as usual. File equals rr.mp3. The file is in the current directory, And with open file, RB, I'm opening the file in read and binary mode as audio file. Next, I'll call client.audio.transcriptions.create, which will return a transcript object. Transcript equals client.audio.transcriptions.create. The first argument of the method will be model equals whisper1 and the file equals audio file. And I'm printing the transcript. That's it. I'm running the code. And we notice that the transcription text is in the text attribute of the transcript object. So print transcript.text. This is the transcription. Very well. We notice that the transcript is quite good. Note that the audio files are currently limited to 25 megabytes and the files that are supported are MP3, MP4, MPEG, M4A, and WAV. We are now taking a break, and in the next video, we'll take a look at how to make translations to English using Whisper. Besides transcriptions, Whisper is also capable of translating into English. Let's go ahead and do an automatic translation. I have this sample audio in German that is a story for children. Let's listen for a few seconds.
Hallo? Oh je.
Toll, Papa. Echt toll hier bei den Löwen. Nur dieser Löwe hier, deiner Beku, ist nicht da. Schläft wahrscheinlich in, oder?
Heute nicht.
If you listen to the file, you'll hear some background noise and other sounds. You might think that could create problems when translating, but that's not the case. Whisper has improved robustness to accents, background noise, and technical language. I'm importing OS, loading the OpenAI API key in an environment variable, importing the OpenAI class, and instantiating the client. The Translations API takes as input the audio file in any of the supported languages and transcribes it into English. I'm opening the file. With open, the name of the file, german.mp3, and RB. I'm opening it in read-only and binary mode as audio file. I will call client.audio.translations.create. So translation equals client.audio.translations.create. The first argument, model equals whisper1, and the second argument is file equals audio file. I am printing the translation. So print translation. And I am running the code. It is running. This is the translation object, and the translated text is in the text attribute of the object. Print translation.text. This is the translated text. It looks pretty good. Okay, we are done. You now have a good understanding of how to use Whisper to transcribe audio into whatever language the audio is in or to translate the audio into English. Hey everyone! In this video, we'll go over the text-to-speech API, which allows us to generate natural-sounding audio from written text, transforming our written content into an auditory experience. This is useful for narrating a written blog post, for producing spoken audio in multiple languages, or for providing real-time audio output using streaming. The text-to-speech API opens up an entire range of applications, including educational audiobooks, interactive voice assistants, accessibility tools for people who can see well, narrative applications for games, stories, and VR. It can bring benefits to language learning with interactive pronunciation guides or content creation for podcasts, video tutorials, and other media formats. Let's go ahead and see how to use the latest API version to convert text into spoken audio using Python. After you import the OpenAI API key as an environment variable, you can define a variable for the text to be spoken by the audio API. Text equals and a text in English. Note that you will be charged per 1K characters. These are the prices for the TTS models, the standard, and the HD1. If you want to calculate the total cost, you can do cost equals len of text divided by 1000 times 0.15. This will be the cost in cents. Don't forget to run all the cells above. It's not too expensive. I'm importing the OpenAI class. From OpenAI, import the OpenAI class. And I'm creating the client object. I am making the API call response equals client.audio.speech.create. The speech endpoint takes three key inputs as arguments: the model, the voice to be used for audio generation, and the text that should be turned into audio. At this moment, there are two models available, TTS1 and the TTS1 HD. For real-time applications, the standard TTS1 model provides the lowest latency but at a lower quality than the TTS1 HD model. Note that in many cases, the audio may not have noticeable differences. There are many voices available. Take a look at them and test different voices in the documentation.
The sun rises in the east and sets in the west. In the heart of the city, there is a large park where people go to relax and enjoy nature.
You should choose the one that matches your desired tone and audience.
The train chugged along the tracks, carrying passengers to their destinations.
The beach was a popular spot on a hot summer day. People were swimming in the ocean.
I will use one of them. The default response format is MP3, but other available formats are Opus for internet streaming and low latency, AAC for digital audio compression, and FLAC for lossless digital compression. I am saving the response to a file, response.stream2file. And the output file will be called tts.mp3. You can use a valid path to create the file in any directory on your hard drive. In this example, the MP3 file will be created in the current directory. I am running the cell. And it's done. In the current directory, a new file called tts.mp3 was created. You can open the file. If you want to play the audio file in Jupyter Notebook, you can do import IPython and IPython.display.audio of the name of the file, tts.mp3. I'm running it.
Future is an open book, filled with chapters yet unwritten, awaiting the brilliance of our minds to paint their stories.
Very well. Note that the voices are optimized for English. However, the model supports many other languages. I will use the same text translated to Romanian, my native language. And I'm running the code. And this is the pronunciation of the text in Romanian.
Viitorul este o carte deschisă, plină de capitole încă nescrise, așteptând strălucirea minților noastre să picteze poveștile lor.
It sounds very well. One final remark. As with all outputs from the OpenAI API, you, the person who generated the output, are the owner of the audio file. However, depending on the country and legislation, you may be required to inform end users that they are hearing audio generated by AI and not a real person talking to them. That's it. In this video, you learned how to use the text-to-speech API to transform text into audio. Thank you. Bye-bye. In this section, I'll show you how to generate original images from a textual description using the DALL-E model and the OpenAI API. But first, let's see what DALL-E is. I will ask ChatGPT. What I want you to notice is that the name DALL-E is a combination of the artist Salvador Dali and the character Eve from the movie WALL-E. So, in a nutshell, the Image API provides you with ways to create original images from scratch based on a text prompt, to edit an existing image based on a new text prompt, and also to create variations of an existing image. DALL-E is just a neural network that was trained to create images from text descriptions. Let's go ahead and see how to generate an original image using the OpenAI API and Python. I am using the latest version of the OpenAI API. You can check the version by running pip show OpenAI. And you should see a version greater than 1. I have imported OS and loaded the API key as an environment variable. Hardcode your API key only for tasks. For real-world projects, load the API key from a .env file using python.env, as we discussed earlier. Now, from OpenAI, I will import the OpenAI class. And I'm creating a client. Client equals OpenAI. I'm calling the constructor of the class. To create such an original image, you'll also need a prompt, which is a text description of the image. This will be the prompt. It will create a photorealistic image of a ginger cat. Note that a new feature in the latest DALL-E 3 API is prompt rewriting, where it uses GPT-4 to optimize all of your prompts before they are passed to DALL-E. In OpenAI's research, It has been seen that using very detailed prompts gives significantly better results. I'm creating the response object. Response equals client.images.generate. The first argument is model. I will use DALL-E 3, but you can use DALL-E 2 as well. So DALL-E 3 or DALL-E 2. Next, prompt equals prompt, the variable I've just defined. The next argument is style and must be one of vivid or natural. Vivid or natural. Vivid causes the model to lean towards generating hyper-real and dramatic images. Natural causes the model to produce more natural, less hyper-real looking images. The default value is vivid. The next argument is size. When using DALL-E 3, images can have a size of 1024 times 1024, 1024 times 1792, or 1792 times 128 pixels. Next, quality equals standard. By default, images are generated at standard quality, but when using DALL-E 3, you can set quality to HD for enhanced detail. Square standard quality images are the fastest to generate. Also note that HD images are more expensive to generate. I recommend you take a look at the image model's pricing to avoid any surprises. These are the prices for the image models. And n equals 1. N means the number of images to generate. Note that at this moment, you can generate one image at a time with DALL-E 3, or up to 10 images at a time using DALL-E 2 with the n parameter. To request more images using DALL-E 3, you should make parallel requests. I am printing the response object. I'm running the code. Good. This is the response object, which is similar to the text GPT response. If you take a closer look at this response object, you'll see the image URL in the value of the URL attribute. This one. So image URL equals response.data, the data attribute, of 0. Data is a list with the generated images, .url. And print image URL. This is the image URL and I'm opening it. Very nice. Note that the more detailed the description in the prompt, the more likely you are to get the wanted results. And for inspiration, you can find some prompts examples at labs.openai.com. Let's save the image to a file on the disk. We can do that by switching the response format from URL to the base 64 encoded image data, or we can leave the URL response format and get the image using the requests library. In this example, I'll use requests because we already have the image URL. I'm importing two libraries, requests and shootil. Shootil is used to copy files. I'm making an HTTP request using the requests library. It's like getting the image using the browser. Image resource equals requests.get of image URL and the stream equals true. stream equals true is necessary to get the raw content of the response. This is an HTTP response object which has a status code. 200 means success, and the codes that start with 4 mean error. I'm sure you are already thinking of the meaning of code 404, page not found, or code 403, which is forbidden. Let's see the HTTP response status code. Print image resource dot status code. I'm running it. It's 200, which means success. If image resource dot status code equals 200, then image underline name equals, and I'm giving it a name. For example, DALL-E 3 ginger cat dot png. I'm opening the file, the image name, in a binary and write mode with open image name and WB, write and binary, as F, and util.copy file obj of image resource .ra and F. I am using util and the copy file object function to copy the raw content of the HTTP response to the file on disk. And else, if the HTTP status code is not 200, I am printing an error message. Print error accessing the image. I'm running the code. There are no errors, and a new file called DALL-E3 gingercat.png was created in the current directory. I'm opening it. Very well. You can also display the image directly in Jupyter Notebook using the pill library. First, make sure that pillow is installed. Run pip install pillow -q. And from pill, written in uppercase, import image. Pill stands for Python image library. And the image.open of image name. And I'm running the code. And you can see the image in Jupyter Notebook as well. We are done. In this video, you learned how to generate original images using DALL-E and how to save them to your hard drive. In the last video, we went over creating original images with DALL-E. Let's go ahead and see how to create variations and edit images using DALL-E. In addition to creating new original images, DALL-E can even modify existing ones, create variations of the images that maintain their features, and interpolate between two input images. Let's see how to create variations of an image with the OpenAI image variations endpoint and Python. Having an image that was generated by DALL-E or not, you can create variations of it. This is the image I have, and I want one or more variations of it. The image should be in PNG format. I have imported OS and loaded the OpenAI API key in an environment variable. I'm importing the OpenAI class and creating the client object. The first step is to open the existing image, as usual, by calling the open built-in function. So image equals open of original _1.png, and the second argument will be RB. The file is a binary one, and that's why I have to open it in binary mode. Next, I'll call client.images dot create variation. Response equals client dot images dot create variation. The first argument image equals image, n equals 1. This is the number of variations to create, and because I pay for each image, n will be 1. And the size equals 1024 times 1024. The size in pixels. And that's it. Let's take the image URL in a variable and print it. Image URL equals response dot data of 0 dot URL and print image URL. I'm running the code. Okay, this is the variation. I'm opening it. This is the variation, and this is the original. Very well. We are taking a break, and in the next video, I'll show you how to edit an existing image using DALL-E. Let's go ahead and see how to edit an existing image. I'll generate a new image using the DALL-E editor interface, which can be accessed at this address, labs.openai.com/editor. If you want, you can generate the image from Python using the OpenAI API, or you can take any other existing image. Here, in DALL-E editor, I'll use the following prompt. John Wick riding a motorcycle on an apocalyptic field in a cyberpunk look, high-quality photography. I'm generating it. Note that DALL-E works better with longer and more detailed input descriptions. Simpler sentences are not good enough because they are way too general. Remember, DALL-E 2 is really good at handling complexity. And I see here some images. Okay, let's take this one. I'm saving the image and moving it to Jupyter's notebook root directory. The image was generated, and though it is good, it is not the best. I want more control over my creative work. For example, I want the image to contain a red moon in an exact part of it. So I want to create a variation of it. To create a variation, I'll need the original image and a mask. The mask is in fact the same image with a transparent area that indicates where the image should be edited. So here in the editor, using the eraser tool, I'll create a transparent area. Note that you can use any image, not only images generated by DALL-E, and you can also create the mask in any other photo editor. I'm saving the mask and I'm moving it to the notebook directory. In the notebooks directory, I have both the original image and the mask. I'm creating a file object by opening the original image as usual. This is the original image, and I'm opening it. Image equals open man on motorcycle.png and RB, the second argument. I'm opening it in binary mode. The image used as the basis for the variation must be a valid PNG file less than 4 megabytes and square. And I'm also opening the mask. This is the mask. Mask equals open mask.png and RB. I'm creating the client by instantiating the OpenAI class. Client equals OpenAI. And don't forget to import the OpenAI class from the OpenAI library. From OpenAI, import the OpenAI class. Now, I'm creating the response object by calling client.images.edit. The first argument image equals image, mask equals mask, and the prompt. The prompt should describe the full new image, not just the erased area. I'm pasting the prompt and adding containing a big red moon. So, John Wick riding a motorcycle on an apocalyptic field containing a big red moon. In a cyberpunk look, high quality photography. I'm adding a \n and hitting enter for a new line. N equals 1, the number of images to generate, and must be between 1 and 10. And the size equals 1024 times 1024. I'm saving the image URL in a variable. Image URL equals response.data of 0.url. And I'm printing the image URL. I'm running the code. This is the image URL and I'm opening it. And we see that the new image contains a big red moon exactly in the transparent area of the mask. Here. That's it. In this video, you learned how to edit and create variations of images using OpenAI's image generation endpoint. In this project, we'll use the OpenAI API and Python to create a healthy daily meal plan. If you are tired of the same meal routine, or if you are struggling to come up with healthy and delicious meal ideas, then AI is the right tool to help you out. First, the Chat Completions API will provide you with original recipes in the style of a talented chef for the entire day based on a list of ingredients and the maximum daily intake of calories. Next, the image generation endpoint will generate original and suggestive images for each meal. Finally, the text-to-speech API will narrate the recipes for you. For each recipe, you will get step-by-step instructions, the total number of calories, the number of servings, the prep time, the cook time, and the total time. You can also specify if the program should use only the provided ingredients or if it is allowed to add others as well. Moreover, you can choose an extra option like spicy, gluten-free, or paleo. Let me show you what we'll do to pique your curiosity. These are the ingredients, and I'm calling the create meals function with these arguments. I'm running it, and in a few seconds, I'll get 3 original recipes in the HTML format for breakfast, lunch, and dinner. This is the HTML code, and I'm displaying it in Jupyter Notebook. Very nice. Next, I'll generate an original image for each meal using the latest version of DALL-E. This is the image for the breakfast. And these are the other images for lunch and dinner. Cool, isn't it? You can use this meal plan for yourself, or you could post it on social media or on your blog. Okay, we'll take a break, and in the next video, we'll start to develop this project step by step. I am starting the project from scratch. I am importing OS and setting the OpenAI API key as an environment variable. Keep in mind that the key should be kept secure. In my case, I will invalidate it after recording this section. I am defining a new function with some parameters that will set how the AI model will generate the recipes for breakfast, lunch, and dinner. So def create meals. And the function's parameters are ingredients, a string with the ingredients that will be used to create the recipes, cal, the total daily intake of calories. The sum of the calories for all meals should be kept below this value. I'll use a default value for this argument, let's say 2000, which is a normal value for an adult. You'll need to keep this value as low as possible if you want to lose weight. Use an online calculator for your specific needs and goals. Here's an example. The next parameter is exact. Ingredients equals false. If true, it will try to use the exact ingredients when creating the daily meal plan. If false, it can add other ingredients for the recipes. Output format equals by default text. A good prompt engineering practice is to specify the format for the output. By default it's text, but you can change it to HTML or JSON. Model with the default value GPT 3.5 Turbo. This is an inexpensive but capable model. Change it to a more powerful one like GPT-4 Turbo only if necessary. System role sets the behavior of the assistant. It's another good prompt engineering practice to specify the role. The default system role will be you are a skilled cook with the expertise of a chef. Temperature defaults to 1 and it can be between 0 and 2. Higher values will make the output more random, while lower values will make it more focused and deterministic. And the extra, by default, none. It specifies extra flavors or the style for the recipes. Here you can specify gluten-free, paleo, spicy, not spicy, and so on. We are done with the function's signature. I'm importing the OpenAI class and instantiating a client object. From OpenAI, import the OpenAI class and the client equals OpenAI. I'm defining a variable for the prompt. This is one of the most important aspects when dealing with LLMs. I will leave it empty for the moment because we'll dive deep into it a little bit later. Next, I am making the API call and creating the response object. Response equals client.chat.completions.create. And the arguments model equals model, our function's parameter, and the messages equals, and a list of dictionaries. The first dictionary, role, system. This is the system role. And the content, system role, the function's parameter. And the second dictionary for the user role. Content, prompt. I am leaving the prompt variable empty for the moment and I'll define it a little bit later. I'm also adding temperature equals temperature. This was the response. I'm returning the assistant's reply. This will be a string. Return response dot choices of 0 dot message dot content. Good. We are done with the create meals function. We are taking a break, and in the next video, we'll dive into prompt engineering and create an efficient prompt for this project. In this video, we'll create the most efficient prompt for our project. We'll dive into prompt engineering, which involves crafting instructions for LLMs to get the desired responses. We'll adhere to the guidelines and tactics for prompt engineering that we discussed in a previous section. Note that it's challenging to generate the ideal prompt on the first try. This is usually an interactive process. You create a prompt, evaluate the results, refine it, observe the new outcomes, and so on. In this instance, the prompt I'll use has already been tested and optimized for the aims of this project. It's not the first attempt. The most important principle is to write clear and specific instructions. Make sure to distinguish between writing a clear prompt and writing a short prompt. We'll use a long prompt to provide more context and clarity for the model, which will lead to a more detailed and relevant output. Always put instructions at the beginning of the prompt, each on their own line, and use delimiters to clearly indicate distinct parts of the prompt. The prompt will be a multi-line string. It will also be an F-string literal. I am starting with the first instruction. Create a healthy daily meal plan for breakfast, lunch, and dinner based on the following ingredients. I'll use triple backticks as a delimiter for the ingredients which are the dynamic part of the prompt. The next tactic is to be specific, descriptive, and as detailed as possible about the desired context, output, or format. Your output should be in the and output format between curly braces. Output format is the function's parameter. The next approach that we'll employ is to explicitly outline the steps needed to accomplish the task. This can make it easier for the model to follow these steps. Follow the instructions below carefully, and the instructions : the first instruction. There's a function parameter called exact ingredients. If true, it will try to use the exact ingredients when creating the daily meal plan. If false, it can add other ingredients for the recipes. I will take this opportunity to use the Python ternary operator, which is useful but not so often used. The ternary operator is a handy tool for simplifying conditional logic and making your code more readable and concise. Let me show you in another cell how it works. It is represented as value equals expression1 if condition else expression2. The ternary operator in Python is a concise way to evaluate a condition and return the appropriate value based on the outcome. It's like a shorter version of an if-else statement, all within one line of code. For example, a, b equals 10, 20, and value equals a less than b. If a less than b, else a greater than b. I am printing the value. I'm running the code. And it says a less than b. It executed this expression, expression1. if A is 100, it will print out A greater than B. The condition was false and it evaluated the second expression, this one. We'll use the exact ingredients function's argument with the ternary operator, like this. Exact ingredients equals true. And I will append to the prompt a string, for example, exact, if exact ingredients, else not exact. So, use only the provided ingredients with salt, pepper, and spices if exact ingredients equals true. This implies equals true. Else, if exact ingredients equals false, I will add to the prompt. Feel free to incorporate the provided ingredients as a base and add other ingredients if you consider them necessary to enhance the flavor, nutritional value, or overall appeal of the recipes. I will continue with some more instructions in a sequential order. The second instruction specifies the exact amount of each ingredient. Ensure that the total daily calories intake is below kcal value, the function's parameter, 2000 by default. For each meal, explain each recipe step by step in clear and simple sentences. Use bullet points or numbers to organize the steps. For each meal, specify the total number of calories and the number of servings. For each meal, provide a concise and descriptive title that summarizes the main ingredients and flavors. The title should also be a valid DALL-E prompt to generate an original image for the meal. And the seventh instruction will be for each recipe indicate the prep, cook, and total time. For the last instruction, I'll use the ternary operator again. If the extra argument is not none, I will add the 8th instruction. So, if extra, this means if extra is not none, add this. If possible, the meals should be, and an extra instruction. Spicy, in the Mediterranean style, and so on. I will go on with another tactic, which is to instruct the model to reason and check the solution before giving it to me. Before answering, make sure that you have followed the instructions listed above. Now, I want to indicate how the answer should end. The last line should contain a string with the titles of the recipes. This is necessary because I need the titles to generate images using DALL-E. The last line of your answer should be a string that contains only the titles of the recipes and nothing more, with a comma in between. I will also employ a technique called few-shot prompting, which means providing the LLM with a few examples of the desired output. I will show the LLM how the last line of its answer should look. I noticed a small mistake. It's messages, not message. The name of the argument of the create method. That's it. It was a long video because prompting is probably the most important aspect when working with LLMs. I'll take a break, and in the next video, we'll test our program. Let's run the program. I'm defining a variable for the ingredients. Foods equals and some ingredients. I'm calling the createMeals function the first time with only the ingredients as an argument and all the other arguments set to their default values. Output equals create meals, and the ingredients equals foods. I am printing the output and running the code. It is running. And I've got a daily meal plan for breakfast, lunch, and dinner. It followed the instructions exactly. For every meal, you see the recipe with a title, followed by ingredients, step-by-step instructions, and the total number of calories. At the end is a summary with the title of the recipes that we'll use with DALL-E to generate images. Let's move on and call the function with different parameters. Output equals create meals, and I use keyword arguments. Ingredients equals foods, model equals, and I use GPT-4 Turbo, which is the most capable model at this moment. Note that only paid accounts can access GPT-4 Turbo. If you use a free account, don't worry, use GPT 3.5 Turbo instead. This is the name for GPT-4 Turbo. Output format equals HTML and CSS. Extra equals spicy. And the exact ingredients equals false. I'm running it again. And I've got the answer in the HTML format. If you want to interpret the HTML code and display as a web page in Jupyter Notebook, use from IPython.display, import display, and the HTML class, and the display of HTML of output. I'm running it. And it interpreted and displayed the HTML code in Jupyter Notebook. Our program works well. In the next video, I'll show you how to generate original images for the meals using DALL-E. In this section, I'll show you how to generate original images from a textual description using the DALL-E model and the OpenAI API. But first, let's see what DALL-E is. I will ask ChatGPT. What I want you to notice is that the name DALL-E is a combination of the artist Salvatore Dali and the character Eve from the movie WALL-E. So, in a nutshell, the Image API provides you with ways to create original images from scratch based on a text prompt, to edit an existing image based on a new text prompt, and also to create variations of an existing image. DALL-E is just a neural network that was trained to create images from text descriptions. Let's go ahead and see how to generate an original image using the OpenAI API and Python. I am using the latest version of the OpenAI API. You can check the version by running pip show OpenAI. And you should see a version greater than 1. I have imported OS and loaded the API key as an environment variable. Hardcode your API key only for tasks. For real-world projects, load the API key from a .env file using python.env, as we discussed earlier. Now, from OpenAI, I will import the OpenAI class. And I'm creating a client. Client equals OpenAI. I'm calling the constructor of the class. To create such an original image, you'll also need a prompt, which is a text description of the image. This will be the prompt. It will create a photorealistic image of a ginger cat. Note that a new feature in the latest DALL-E 3 API is prompt rewriting, where it uses GPT-4 to optimize all of your prompts before they are passed to DALL-E. In OpenAI's research, it has been seen that using very detailed prompts gives significantly better results. I'm creating the response object. Response equals client.images.generate. The first argument is model. I will use DALL-E 3, but you can use DALL-E 2 as well. So DALL-E 3 or DALL-E 2. Next, prompt equals prompt, the variable I've just defined. The next argument is style and must be one of vivid or natural. Vivid or natural. Vivid causes the model to lean towards generating hyper-real and dramatic images. Natural causes the model to produce more natural, less hyper-real looking images. The default value is vivid. The next argument is size. When using DALL-E 3, images can have a size of 1024 times 1024, 1024 times 1792, or 1792 times 128 pixels. Next, quality equals standard. By default, images are generated at standard quality, but when using DALL-E 3, you can set quality to HD for enhanced detail. Square standard quality images are the fastest to generate. Also note that HD images are more expensive to generate. I recommend you take a look at the image model's pricing to avoid any surprises. These are the prices for the image models. And n equals 1. N means the number of images to generate. Note that at this moment, you can generate one image at a time with DALL-E 3, or up to 10 images at a time using DALL-E 2 with the n parameter. To request more images using DALL-E 3, you should make parallel requests. I am printing the response object. I'm running the code. Good. This is the response object, which is similar to the text GPT response. If you take a closer look at this response object, you'll see the image URL in the value of the URL attribute. This one. So image URL equals response.data, the data attribute, of 0. Data is a list with the generated images, .url. And print image URL. This is the image URL and I'm opening it. Very nice. Note that the more detailed the description in the prompt, the more likely you are to get the wanted results. And for inspiration, you can find some prompts examples at labs.openai.com. Let's save the image to a file on the disk. We can do that by switching the response format from URL to the base 64 encoded image data, or we can leave the URL response format and get the image using the requests library. In this example, I'll use requests because we already have the image URL. I'm importing two libraries, requests and Shutil. Shutil is used to copy files. I'm making an HTTP request using the requests library. It's like getting the image using the browser. Image resource equals requests dot get of image URL and stream equals true. Stream equals true is necessary to get the raw content of the response. This is an HTTP response object which has a status code. 200 means success, and the codes that start with 4 mean error. I'm sure you are already thinking of the meaning of code 404, page not found, or code 403, which is forbidden. Let's see the HTTP response status code. Print image resource dot status code. I'm running it. It's 200, which means success. If image resource dot status code equals 200, then image underline name equals, and I'm giving it a name. For example, DALL-E 3 ginger cat dot png. I'm opening the file, the image name, in a binary and write mode with open image name and WB, write and binary, as F, and shutil.copy file obj of image resource .ra and F. I am using shutil and the copy file object function to copy the raw content of the HTTP response to the file on disk. And else, if the HTTP status code is not 200, I am printing an error message. Print error accessing the image. I'm running the code. There are no errors, and a new file called DALL-E3gingercat.png was created in the current directory. I'm opening it. Very well. You can also display the image directly in Jupyter Notebook using the PIL library. First, make sure that Pillow is installed. Run pip install pillow -q. And from PIL, written in uppercase, import image. PIL stands for Python Image Library. And the image.open of image name. And I'm running the code. And you can see the image in Jupyter Notebook as well. We are done. In this video, you learned how to generate original images using DALL-E and how to save them to your hard drive. Welcome back. We've created a function that takes some arguments and, using an efficient prompt, calls OpenAI's GPT model to generate a meal plan for the entire day. We've then generated images for the meals using DALL-E. Next, we'll go ahead and use the text-to-speech API to narrate the recipes. This is useful in many cases. Maybe you are driving and aren't allowed to read, or you simply don't see well. The GPT model returns all 3 recipes in its output. We need a way to split them into the recipes for breakfast, lunch, and dinner, because the text text-to-speech model will narrate only one. There could be more approaches, but what I'll do is change the prompt to add a separator between the recipes. I'll add to the prompt the 9th instruction. Separate the recipes with 50 dashes. I'm also changing here, points 1 to 9. I'm running it again. And we see how it separated the recipes by 50 dashes. That's good. We'll split the output, the recipes, into a list using the 50 dashes as a separator. Meals equals output dot split of dash times 50. Let's check how many elements there are in the list. Len of meals. There are 4 because there's a separator, 50 dashes, before the last line of the answer, which contains the titles used by DALL-E. Here. Let's see the recipe for the breakfast. This is the recipe for the breakfast. This is for the lunch and for the dinner. What I'll do next is an optional step. Sometimes writing a text concisely using bullet points or numbered lists doesn't translate well to spoken language. Natural speech requires connecting words and phrases for a smooth flow. Additionally, the GPT model's response included irrelevant sentences about the recipe. For instance, the first sentence, "Here is a healthy daily meal plan based on the provided ingredients," is unnecessary. To address these issues, I'll make a new API call to the GPT model and provide the concise recipe text. This text. I'll ask the model to adjust the recipe for a more natural flow when spoken aloud. I will prompt the user for the recipe to be narrated. You can also speak it loud and then transform the spoken language into text using the Whisper model. Meal equals input of, enter meal's name. And if meal.lore, I am testing the lore version of the string. Maybe the user entered the meal in capitals. I'm also calling the strip method. Maybe there's an extra white space at the beginning. Equals breakfast. If the user entered breakfast, recipe equals meals of 0. If the user entered lunch, recipe equals meals of 1. And finally, if the user entered dinner, recipe equals meals of 2. If the user entered something else, recipe equals invalid recipe. Now the prompt. This is an example of a prompt. Of course, you can change it and experiment with different outcomes. I will provide the recipe that will be spoken aloud. If necessary, you will adjust the recipe to make it more readable. You can also add an introduction and summary, but you won't change the ingredients, instructions, or other key elements of the recipe. And recipe: recipe in curly braces. I imported OpenAI and defined the client in a cell above, but I will do it again here because I want you to have the entire code in this cell. I am making the API call. client.chat.completions.create. Models GPT 3.5 Turbo, and messages. I'll use only the user role. And the assistants reply. Let's say spoken recipe equals response dot choices of 0 dot message dot content. I'm running the code and I'm entering breakfast. I am also displaying the spoken recipe. The narration looks more natural. This is the text that will be narrated, and this was the original recipe. I'm defining a function that takes a recipe as input and generates an audio file in the MP3 format. df speak, recipe and file name. I'm importing OpenAI and defining the client. Now, I'm making the API call to the text-to-speech model. Response equals client.audio.speech.create. Model equals TTS1. Voice equals, and I'll use one of the available voices. And input equals recipe. I'm saving the response to a file. Response.stream to file of file name. Very well. I'm running the code. I'm defining the file name and calling the function. File name equals and an f string. Meal, what the user has entered, breakfast, lunch or dinner, .mp3. And speak of spoken recipe, the text, and the file name. I'm running it. It is running. Now it's done, and a new MP3 file has been created in the current directory, breakfast.mp3. It can be opened or played in Jupyter Notebook using this piece of code. Import IPython and IPython.display.audio of file name. I am running it. Let's hear the recipe.
Introduction. Eating a healthy and balanced meal is essential for starting your day off right. In this recipe, we will guide you through a delicious Mediterranean vegetable omelette that is packed with nutrients and flavor. With colorful vegetables and protein-rich eggs, this breakfast will provide you with the energy you need to tackle the day ahead. Let's get cooking. Ingredients: 1 tablespoon of olive oil.
Very well. We are at the end. In this project, I showed you how to create a healthy meal plan for the entire day based on some ingredients and the total amount of calories. I've also shown you how to generate original images for each meal using DALL-E and narrate a recipe using the text-to-speech model. You can incorporate this into your blog or share it on social media.
Nice work! You've just taken your first real steps into building with AI. You now know how LLMs and APIs work. You've practiced with the OpenAI API in Python, and you've built your own project. That's huge. But this is only the beginning. From here you can go on to build chatbots, search systems, multi-step agents, even full-blown research assistants powered by LLMs. If you're ready to dive deeper and take the next step, then check out Andrei's full AI Applications Bootcamp course, where you'll dive into tools like LangChain, LangSmith, and LangGraph to build production-grade projects. If you enjoyed this crash course, please drop it a like and leave a comment with your questions, thoughts, or feedback down below. That's it from me, and I look forward to seeing you inside the Zero to Mastery Academy.